Fix my displays real quick here.
You need to pick a clip.
So I always get this question, I can never remember the answer. Who remembers who has the egg with the penguin feet for a logo? Somebody in this room has got it.
That's a t-shirt question.
Yeah. Is that the Java character?
Duke.
It's not Duke. It's not Duke.
No.
It's not Duke.
No, it's Tuck's feet coming out of an egg. It's some distro, and I can't remember which one. And now I have passed my pain on to you.
Thank you. And that's a GNU, right?
Yeah, there is a GNU up there.
Who's got
Alright.
the spear?
And of course, BSD.
Who's the
Yeah,
spear?
Beastie is up there.
Beastie's up there.
Who's the
The
little
one on the
guy?
right.
The little bird.
The little guy is Gentoo, I believe.
Who's the guy on the right with the spear?
That's Tux.
That's Tux.
That's
Tux.
just generic old
That's
Tux.
not-
And that's a Debian logo up there on the war banner that they've got there.
I've got a very good question for you. Why wasn't the Windows one driven off the cliff first?
Aerodynamics.
They're all
I don't know, man. I mean, if you put them both side by side, and you know, I was standing there with the size 10 combat boot, I don't know which one I'd go for first.
Okay.
You're trying to pull off some kind of kung fu like double kick thing. I don't
I'm
know.
just trying to start a fight.
I know there are a lot of folks who are, you know, big Apple fans and apologists, and I see some glowing fruit in the room, but I'm not one of them. All right, folks. So, welcome to Storage 101. How do I shot RAID? I am a longtime sysadmin, big open source guy, own small businesses, do a lot of talking and boring people and whatever I'm going to do tonight. You'll be able to find the slides for this and all of my decks at openoid.net/presentations. Tonight's aren't there yet, but they will be. I keep them in a couple of places, and I forgot to upload it to that one, but I'll take care of that. Please do ask questions. If you ask questions as I'm going through this stuff, I have a monster of a slide deck here, but I also tend to talk extremely fast and burn through a whole lot of information. It will not upset me if you ask questions, and as Todd told you, you may actually get a shirt out of it. I might tell you, hey, hang on, we'll get to that later, but other than that, just, you know, ask questions, don't be afraid. The first thing, the biggest thing that I see people screwing up when they talk about storage is, you know, they want to talk about throughput. How many megabytes a second do I get? And you hear these misconceptions like, oh, like I have this 8-disk RAID 5 and it's like super, super fast because, you know, that way I get like the speed of 7 disks at once. I hear a couple of snickers here and there through the audience, but honestly, you should all be in uproarious laughter right now because that's not how it works. The spec that really, really matters when you're talking about how well storage performs is not throughput, it's IOPS. IOPS is an acronym that stands for Input Output Operations Per Second. And so the thing is, you always care about how many megabytes per second you can get out of something. But the tricky part is, like if you were to go to a hard drive manufacturer's website or go to a consumer PC magazine that says, hey, here's this list of hard drives ranked, and you see like, you know, this long laundry list of hard drives, and you see a column right next to it, it's like, this one gets 200 megs a second, this one gets 188 megs a second, whatever. Those are under completely ideal conditions where that drive is not bottlenecking under IOPS. And you don't really care about that because the slowest one of those hard drives, when it's producing that top speed number, be it 120 megs a second, 150 megs a second, whatever, you're happy. You're not angry with it. When you're angry with it is when you start getting bottlenecked on IOPS. You bottleneck on IOPS when you're no longer just reading all of your data in a nice steady stream from A to B. Instead, you've got, you know, more processes trying to read from the disk at once. Well, that's time shared, right? If you've got 5 different people that want to read a lot of data from the disk at once, you can't just read all of it in a nice steady line. You read a little bit of it for, you know, person 1, and then you skip the head over here to read a little bit more for person 2, and skip it over there, and you keep doing this all back and forth, and now you're bound by IOPS. You're asking the hard drive to do lots of different things. It's having to seek the heads back and forth, trying to do all these things at once, and your performance absolutely goes off the cliff. The more write processes you have, again, you're more operations needed. As your data gets more fragmented, it's no longer written in a straight line around the disk. You got to go hunting for it. Everything sucks. When you've got smaller block sizes of data that you're looking for, like a database or a mail server that's having to pull like little bits of data and write little bits of data all over the place, again, you're going to bind on IOPS. How do we get more IOPS? Well, you can have faster disks. You can have more disks. You can have a better topology, one that provides more IOPS with the amount of disks you have. You can have a smarter topology, one that actually makes an effort to write things in a better order or figure out how to aggregate things properly. You can have faster disk controllers. You can also try to reduce how many IOPS you need. If you've got a big, smart...
What is more? Is this
What was that?
AR?
Go back to the previous slide.
Joke?
That's a joke.
That's a joke.
That's internetese.
Is it an acronym for something? Or
Oh no, absolutely not.
Absolutely not. All right.
It is just being silly.
Or!
So there's a
Just
difference
like
between the
Ed.
word more and more. That's more IOPS.
Most of us here can't spell, so we didn't say. All right, thank you.
That's the truth.
That is the truth.
Yeah.
All right. You can also try to reduce the IOPS you need to do the same task. If you have a great big read cache, so that the second, the third, and the fourth, and the fifth time somebody goes to read the same data, you don't actually have to go to the disk for it because you still got it in RAM. Well, that's that many fewer IOPS that you have to inflict on your storage. So that reduces your needs. If you do write aggregation, say you've got 30 different people that are all trying to write little bits of data to the disk, rather than just immediately writing this here and that there and that there and that there and that there, you just kind of coalesce it in memory for a while until you've got a nice big chunk of it and then write it all out at once. That's a lot fewer IOPS. And when you're doing write coalescing, that also means you're liable to have less fragmentation because you can write this stuff in a nice smooth stream when you do. But where are the IOPS cliff? So when you do all these things, you've got a nice big read cache and you're doing write aggregation, you're doing write coalescing, you're not actually sending all that many IOPS out to your storage. Everything looks peachy keen and everything's fast, but the problem is then all of a sudden your users go off cache. They start asking for data they've never asked for before, they start making a lot more writes than what you're expecting, and now all of a sudden your performance doesn't just get a little bit slower, it goes from up here to way down the weeds down here, and people actually think the system has crashed sometimes it gets so bad. So we talk about types of disks. Conventional disk. When somebody says a hard disk, they usually mean conventional. It's spinning motors. The data is actually stored on platters with literal, it's iron oxide, the non-fancy term being rust. You magnetize rust on a spinning disk and you got a head that moves back and forth over it. It's total Flintstone stuff. There's so many things that go wrong. It's ridiculous. Now, your best case on a conventional disk, when you're doing that mostly contiguous reading or writing, but everything can just the head can kind of stay put and let the disk rotate underneath it and read or write from it. You might get 150 plus megabytes a second. Really fast drives, you might maybe see 200. More typically, you don't usually have that best case where you can just read everything all in line and write everything all in line. You're doing a fair amount of seeking, and your performance plummets, from that 150 plus down to most of the time, most of the day, you're going to see like 30 megabytes a second, not 150. When things really get bad, you will actually go down to under 1 megabyte per second on the same drive. When you start doing really small block random I/O, and again, that's what we're talking about when we bind on IOPS. Now all of a sudden you're looking at this drive that was giving you 150 or 200 megabytes a second of data. You're choked down to, like dial-up internet speeds. That's the point at which you want to pick up your laptop and throw it through the window because you try to type and the menu won't come up, nothing's happening. You're like, what is wrong with this thing? It's pretty much always the storage. So these days you shouldn't really be using Rust much unless you have a really big storage array that's storing a whole lot of data, many terabytes. You should be looking at solid state disks. They're more expensive than conventional disks, but not that much more anymore, and you get an awful lot out of it. You no longer have the ridiculous Flintstones spinning platter with a moving head and a motor. Yes?
Okay, I got a LULZ.
LULs. It's just a corruption of laughs. LOL is laugh out loud, and LULs is just pronouncing You're not getting t-shirts for these, man.
He's just trying to keep up.
I appreciate your interest, just, yeah.
What is the circuit?
That particular circuit is a,
It's not a NAND gate, is it?
no, it's not. I believe it was a tri-state amplifier, if I recall. Honestly, it was a licensed for reuse with modification circuit diagram that I could easily invert and put on that slide. That's exactly what it was. The whole point is there's no moving parts there, and that's all that's really supposed to represent, because in a solid state disk, there are no moving parts. It's all electronic. So now it is, you do have, with solid state disks, you have different cases where you don't get the top performance out of it. When everything's going perfect on a typical solid state disk, you may get throughput of up to 500 or even more for really fast ones, megabytes per second. But here's where it gets more interesting. Your typical case on the solid state disk is going to be 100 plus megabytes a second. And even your worst case, for most decent SSDs, you're still going to be up around 50 megabytes a second, faster than that hard drive was in its typical case, let alone its worst case. So it's a really big deal. Now, when you talk about, why isn't everything just always best on the solid state drives? It's because the solid state disk isn't really just one chunk of storage. It's got a smart controller, and on the inside of it, it's actually kind of like a little RAID array in there. You have multiple banks of NAND flash storage, and when you've got that super fast 500 megabytes a second or whatever, what's happening there is you're actually storing or retrieving your data evenly across all those banks of NAND flash. But if you end up needing to get a whole bunch of it from one bank, or maybe you're trying to access the disk when there's a garbage collection routine going on in the background, or all these kinds of things, that's when your storage speed can dip down on it. Now, when we look at actual IOPS, the most IOPS that you're going to get out of a conventional disk is going to be somewhere between 50 to 200 IOPS. When you're actually bound on IOPS, you're going to plummet down as low as 0.2 megabytes per second. Your absolute best case on a super fast enterprise drive, you might hit 200 megabytes a second. Versus you look at the solid state disks, you're looking at 50,000 plus IOPS all day long, and you'll be looking at speeds of 50 to 500 plus megabytes a second. And when I say 50,000 plus, I mean, so look, we're comparing 50,000 or more IOPS versus 200. You might think, okay, well, that's probably like, he's picking the fastest thing out there, right? No, 50,000 IOPS is a slow SSD. Fast consumer SSDs will typically do anywhere from 90 to 120,000 IOPS versus a good consumer hard drive should do somewhere over 100. So it's a huge, huge difference. All right. So you can get faster storage by having faster disks. And before we move completely on from that, though, I want to also put to bed, if you look at conventional hard drives, people will make a big deal out of, oh, this one's 5,400 RPM, or oh, that one's 7,200 RPM. This screaming demon of a Cheetah over here is 15,000 RPM spindle speed. Now that does make a difference, but it's a small difference. That's the difference between the 50 to 100 IOPS or the 200 IOPS, or the big crazy thing that sounds like a jet turbine when it spins up in your machine. All right.
I have a question.
Yeah.
So whenever SSDs first came out, I read on the internet that if you left a certain portion unallocated, then the disk would optimize and use that for caching. Is that still the case today, or was that a myth?
Well, so you don't quite have it right. There's a grain of truth there, but what actually happens is if you limit the amount of space that you write to the SSD, what you're doing is you're leaving more of it available to replace bad sectors with later, and you're giving it more headroom to be able to rebalance the data. I mentioned those garbage collection routines that can run in the background. It's not just a disk. An SSD is really kind of a little computer all in its own right. It's a storage system, and the controller does stuff that you have no idea about. And when you limit the amount that you write to it, you give it more headroom. It makes it more efficient for it to shuffle things around between those banks of NAND. So it does help. Under provisioning can also extend the life of the drive, but it's really not anything to do with caching. Does that answer your question?
That's really helpful. Thank you.
Okay.
Under provisioning is what it's called.
Yeah, under provisioning. When you make a small partition on it and you only write to that, and by the way, the partition actually really doesn't matter. You can have the exact same effect by just not saving that much data to the thing to begin with.
Gotcha.
All right, so actually talking about topology, so now we're going to talk about when you got more than one disk. That's what we're referring to when we talk about storage topology. And your simplest one is, well, you don't have more than one disk. It's just a single disk. For a single disk, you have 1D IOPS, and you're going to see this a lot for the next few minutes when we talk about these topologies and what you can expect in IOPS. Remember, the thing about IOPS is I don't actually care, and you don't actually care directly how many IOPS a topology or a disk is capable of. IOPS are really a measure of how far in the weeds we can get before we murder our throughput. So the more IOPS we have, the better this device is going to behave when you get down to these really, really difficult to fulfill storage requests like databases or booting an operating system or serving people's home directories, anything with little tiny files, that kind of thing. And you're going to see this D notation where I refer to a generic disk. So whatever disk it is you're using, whether it's a conventional disk that provides about 200 IOPS or whether it's an SSD that provides 50,000, D is just going to refer to one of those. All right. So our simplest topology, once we move beyond a simple disk, is RAID 0. RAID 0 is a simple stripe, which means that let's say that you've got a bunch of 4K disks, meaning they have 4K sectors on each individual disk, and you've got 6 drives in a simple RAID 0 stripe. Onto it just right. Very quickly, you will find that all of a sudden you're bottlenecking on IOPS, not throughput, and now it's acting like a single disk. So that's classical RAID 0, which you're never going to run into these days. You're going to run into this block level round robin JBOD. People will call it a stripe, and it's not really true because in this modern implementation of RAID 0, it's really going to just put blocks where they're supposed to go. It's going to have an allocation table, and it's going to say, block 0 of 50 bajillion is actually on this disk right here, and block 1 of 50 bajillion is on that one right there. And it really will do individual block writes to individual disks. So it can grab each one off of each disk. It doesn't have to light it up in stripes. It just grabs each one at each time. Because of that, in this case, we're going to trend towards N, the number of disks in your array, D, what you get off each disk, IOPS. So 8 disks in a modern RAID 0 will truly be as fast as 8 disks. Now, the unfortunate thing is, if you lose any one of those 8 disks, you just lost everything. It's all gone. So RAID 0 is a great way to get fired in production. All right, so we talk about storage efficiency. Any RAID 0, whether it's classic or modern, is going to trend towards ND storage, which is the same concept. However much storage you got on one disk, multiply that by how many disks you got in the array, you didn't lose any efficiency, which is because you don't have any redundancy, which is because you have now, if you've got an 8-disk RAID 0, you have now multiplied your chances of hard drive failure by 8, which means next year you're fired. Yeah, it really wants to eat all your data. You're going to get fired. Don't do this. You also will not be able to collect unemployment because you'll be terminated for cause. You were a dumbass. You should know. Obviously, there is a place for RAID 0 if you need incredibly rapid access to ephemeral data, stuff that you just need it for right now. If you lose the whole thing, it doesn't matter because you had it all in slower storage somewhere else, or it's temporary data that won't be worth anything after tomorrow, then RAID 0 is a great answer. Just make sure that, yes, you really are okay with losing that data, because you really will. All right, so I mentioned that word JBOD. I said modern RAID 0 isn't really a stripe at all. It's a JBOD. It's an acronym for just a bunch of disks. And all you really need to know about JBOD is it means nothing other than just a bunch of disks. There's no definition to how those disks are accessed. That's the whole meaning of JBOD. Who knows? It could be file level, it could be block level, it could be something completely different. It could be round robin where you go evenly from one disk to the next. It could be sequential, like you do everything on one disk and fill it up before you go to the next one. It could go to the least busy disk, it could go to the disk with the most available space, or something completely different, who knows? And answer your question, sir,
Yes.
What are they?
what the heck, laugh out loud, oh my goodness, barbecue, or other.
Yeah.
All right, So there are no guarantees of survival of JBOD on loss of disks or corruption on the disk. Some JBODs may actually be resilient. They may be very resilient. They may have lots of redundancy built in. Most aren't. Most don't have any resiliency at all. They may or may not be storage efficient. They may or may not be performant. You don't know because it's JBOD. If somebody tells you this is a JBOD, you have to ask them questions because there are no guarantees implicit in that word. All right, let's move on from RAID 0 and JBODs and go to RAID 1. Simple mirror set. This is also just antediluvian ancient storage topology, but it's really, really useful. So you'll still see it a lot today. Simple mirror set just means you got disk 1, you got disk 2. Every time you write a block, you write the same block to disk 1, you write the same block to disk 2. When you go to read it back, you don't have to light up both disks at once. You can read it off of whichever one happens to be available. So for writes, it doesn't give you any extra efficiency. For reads, it's nice and performant. And the best thing about a RAID 1 is if you lose either one of these disks, just go chuck it in the toilet and flush. It doesn't matter because this one has all the data that one did. Now, another thing that some people don't realize is while you will most frequently see RAID 1 mirrors in pairs, they don't have to be. You can encounter a 16-disk RAID 1 where all of 16 disks each have the same block on there, and they are stupid fast to read from because you literally have ND IOPS. You know, then if you have to actually write to it, then it's still going to perform like a single disk because you got to light up every single one of them to commit that block. So, yes.
Back up. Divide by 2, should that be divided by D?
Yes, it absolutely should. There actually is down there. It can be, oh, well, I should have said that. I thought I had an asterisk on there that said assuming 2-disk mirror, but you're correct. That should absolutely just be N. Well, actually, it should just be D.
Yeah.
Trends towards D, right?
Oh, I'm sorry. Yeah.
Well, and you were still correct. You know, ND divided by N. Well, you said ND divided by D. It would be the ND divided by N, which is D. Enough about the D. All right, so offers 1 disk worth of storage, period. Doesn't matter how many of them that you have, that's it. And for survival, RAID 1 is fantastic because there's no reconstruction from parity or any kind of weird, behind the back calculations you got to do to get your stuff back. Any single one of those disks can just be chucked into a machine and mounted. It's good to go. There's no funny business. So nothing survives better than RAID 1. All right, so RAID 10, it starts to get interesting. Now we're actually combining these two classical topologies. We're combining striping and we're combining mirrors. So again, way back in the day, when I rode my dinosaur to sysadmin school, people would get confused about the difference between RAID 0.1 and RAID 10 because one of them is a stripe of mirrors and the other is a mirror of stripes, and it would get really confusing. And the real answer there is you will never, thankfully, see RAID 0.1 in your life anymore because it's not the late 80s or the early 90s. RAID 10 is a stripe of mirrors, meaning you've got mirror pair here, you got mirror pair there, you got mirror pair there, and then you stripe across all 3 of those things. So what that means in terms of, we'll actually talk about the storage first. So you've got 6 disks, but you've got the capacity of 3 of them in this, theoretical, and it can be any number, but say we've got a 6-disk RAID 10 and 2-disk mirrors. So we've actually got 3 individual mirrors in there. Each one of the disks in each of those mirrors has the same data. So these 2 have the same data, these 2 have the same data, these 2 have the same data, and you do a simple stripe across the top. So for storage, you're going to have, this is where I remembered my asterisk being, you've got ND divided by 2, assuming you're doing 2-disk mirrors. It's possible to do RAID 10 with bigger mirror sets. You can have RAID 10 with 3-disk mirrors, 4-disk mirrors, whatever. But this kind of gives you a nice combination because you've still got that really simple type of redundancy. You can lose any one of the disks out of those mirrors, and I'll get to you in a second, and the array will survive. However, if you lose all the disks out of any of those mirrors, everything's gone. Yes, sir, in the back.
So what happens when you lose a disk in a mirrored environment? Because it seems to me there's got to be some recovery time. You say you just plug the disk in, no behind the back calculations, just get access to your data. But now
You never lost it to begin with.
well, when you write new data, well, you've lost redundancy though, right?
Yes, you have no redundancy until you replace that disk.
So, when you put a new disk in place of the failed disk,
It'll copy all the data from the surviving disk onto the new one.
but there's a period of time when it does that, right?
Sure, but there's no parity calculation, and very importantly, you're not lighting up any of the other disks in any of the other mirror pairs, trying to like read everything and then get your parity and build a calculation off of here and figure out what you need right over there. You're literally just cloning thing from A to B all the way down. It's a very fast, very simple operation. All right, so performance of RAID 10. RAID 10 is one of your most performant possible types of storage topology. You will trend towards the entire number of disk of IOPS for read, because anytime you want blocks, you can just grab it from the disk. You'll trend towards ND divided by 2 IOPS write, so basically for each one of your mirrors. If you've got a 6-disk RAID 10, which is 3 mirrors, then you will trend towards 3 disks worth of IOPS for writes. For reads, it's faster because for every one of those mirrors, you can read from either disk on the mirror. Yes?
How do different disk types and capacities affect the both IOPS and storage? If I had a hard drive that was 1 terabyte and then an SSD that was 250 gigs, how would that affect the storage?
You would not put both of those in the same classical RAID array, and if you did, because you were incredibly dull, you would have the absolute worst characteristics of each drive. So you would have the smaller capacity of the SSD bottlenecking your whole RAID on storage, and you would have the incredibly slow speed of your hard drive bottlenecking on performance. So yeah, don't do that. It's a terrible idea.
It already sounds bad even just thinking about it.
Yeah, it should. You should feel kind of itchy, like you need a shower.
But,
I already did that.
but another part of his question is mixing different sizes.
Yeah, I covered that. So it's the worst of the worst. Your smallest disk is going to determine the size of the whole array. You're going to be throwing away the extra space on all your big disks. And your slowest performer is going to bottleneck the whole array, because every time you got to read something, it's going to slow down until it can get done with it. So yeah, just don't.
We'll move on to some other strategies where something like that can be used for caching content.
We'll get there.
Yeah.
We'll get there. All right, so RAID 10, you've got number of disks divided by 2, assuming they're 2 disk mirrors storage. You can survive any single disk failure, and you can survive any number of failures as long as you've got at least 1 disk surviving in each mirror. The minute you lose all the disks in 1 mirror in a RAID 10, you lost the whole thing. It's all done. Because your blocks are striped across those mirror sets, including the metadata for your file system. So if you've got 2 disk mirrors, if you lose a whole mirror, it's all gone. You can calculate this. If we're assuming 2 disk mirrors, you can use this nifty little formula here to figure out what your odds of survival are. So for example, if you got 2 disks failing in an 8-disk RAID 10 with 2 disk mirror sets, your odds of surviving a third failure are, do the math, comes down to 2 out of 3. So these things they're pretty freaking resilient. Having 2 out of 3 odds for losing 3 out of 8 disks is not that bad. All right, RAID 5. I would love to say that you probably won't encounter this all that much, but the odds are if you do anything with storage or with small business servers, you'll see it over and over and over again, and it just needs to die. RAID 5 is a stripe much like classical RAID 0, but it introduces the concept of parity. The parity is not a single disk. That would be RAID 3, which you'll probably never see, thankfully. With RAID 5, let's say you've got 4 disks in a RAID 5 array. So you're striping your data, right? You're in a block here, or a block here, or in a block here. Okay, that's 3 out of your 4 disks. On your 4th disk, you're going to write a parity block. You're going to do basically a simple XOR of all the data on disks 0 through 2. And you're going to write that to that block on the 4th disk over here, disk 3. Now, which disk has the parity block? It's going to kind of go in a checkerboard as you write down there, so it's not all on any one disk. But at the end of the day, what that means is if you lose 1 disk, then you're going to be able to recover all the data that was on that disk. For the spaces where that disk had the parity block, doesn't really matter, you didn't need it. For where that you had a data block on that disk, well, it will take the remaining 2 data blocks and that ECC check, the error correcting checksum, the XOR over on the parity block, and it does a little simple Boolean math on that, and it reconstructs what should be in that block, and you can keep limping on along. This will consume some CPU. When you go to replace that disk, it just kind of does it backwards. It will go through and it will reconstruct the parity to write on there where you're missing parity, and it'll reconstruct the data to write on there for the other. It'll reserve the whole thing down. You're good. You see a lot of RAID 5 out there in the world because it's cheap and it's simple and it's easy, and people have this idea that, oh, if I've got an 8-disk RAID 5, well, I understand I'm giving up 1 disk worth of parity, so I'm losing that for storage, and I understand I'm giving that up in performance, but hey, I'm still as fast as 7 disks. You are not. The worst case here is when I say trends toward 1D IOPS on a RAID 5, I mean you won't ever quite get there. When you really push a RAID 5, it's going to be slower than a single disk would be out of that array. The reason for that is, on any given stripe read or write, you are not just as slow as a disk of the type that's in the array, you're as slow as the slowest disk for that particular operation. If one of those things is having a bad day and has to reread a sector twice or rewrite one twice or had a longer seek to get there than the others, you're going to bind on that. So you're binding on the slowest of your 8 disks every single time when you're down there in the weeds on IOPS. So RAID 5 performs terribly. You will see many junior and unfortunately a few senior sysadmins who will set up RAID 5 and put a database on it. Horrible idea. Horrible. So RAID 5 is going to trend towards N-1 storage. If you got 8 disks in a RAID 5, you'll trend towards 7 disks worth of storage. You usually won't quite get there because there's a little bit of overhead involved, but you'll get pretty close. You can survive any single disk failure just fine. As soon as you have a second disk failure, you're dead, period. All right, RAID 6 is just like RAID 5, except you got 2 blocks of parity. If I really wanted to bore you, I would put the equation up there for how you actually get dual parity, because it's not just writing the same parity block twice. You actually have to have something that you can reconstruct your data from, whether you're missing a parity block or whether you're missing 2 data blocks, because RAID 6 can recover from any 2 disk failures. I've seen the equation. I have not memorized the equation. I have frankly not bothered to completely understand the equation. I just know it works. So it's still basically an XOR kind of a thing. It's Boolean math. But basically with the RAID 6, you will be able to recover from losing any 2 disks. After that, it's dead, just like the RAID 5 would be. And again, we're still just trending towards 1 disk worth of IOPS. Trending towards your number of disks minus 2 worth of storage, not a big surprise there. And we already covered failures because I like to do my slides out of order. All right, RAID 50. Hopefully you'll never see this. It's a stripe of RAID 5s. I have seen these. Some enterprise storage, like enterprise hardware RAID controllers that have lots and lots of SAS or SCSI ports on them, will be set up able to do RAID 50, where you have a stripe of RAID 5s and you're trying to kind of get the best of a stripe of the stripes, and it's a horrible Rube Goldberg. There was a time this made,
Go buy an SSD.
Yeah, buy an SSD and eat its lunch. Other than storage capacity, that's the thing. I mean, you would normally do this when you needed really massive amounts of storage capacity, which is why you should never see that now, because if you have so many disks that you might be thinking about doing a RAID 50, you should really be doing something modern instead. You should be building a distributed file system, a clustered file system, look into Lustre or Gluster or whatever. Just don't go out and get some Dell monstrosity with a RAID 50 controller.
Is it worse than Drobo?
It's that's a whole different. I mean, Drobo is something that normally you're only going to see in somebody's house, whereas RAID 50 is something you're normally only going to see in an enterprise with a sysadmin who hasn't learned anything in 20 years. All right, so does anybody have any questions about any of the classic stuff that I just kind of breezed through before we get to the fun stuff, the modern file systems? This would be a great time if anybody's got any questions about any of those basic topologies. Anybody? You, sir.
What's the difference between RAID 3 and RAID 4 again?
I forget what RAID 4 is.
I thought RAID 4 was the parities on a single disk.
No, that's RAID 3.
No, RAID 4, because that's what that plus.
There's a difference because RAID 3 is what FreeBSD used to use instead of RAID 5, and I used that for years. I am positive that their implementation of all the parity on one disk is RAID 3. I forget what the difference between RAID 3 and RAID 4 is. Yeah.
That's what they had. They had one disk with parity, and the rest were just
Yeah, that's also what RAID 3 is. There is an arcane difference between 3 and 4. I don't remember, but the big difference between either of those and RAID 5 is RAID 5 checkerboards the parity rather than putting it all on one disk, and the reason for that is better performance when you're running degraded.
So two things that you didn't mention is offline storage, and you know, from yesteryear, but still, I think people have massive data that they wouldn't mind keeping offline. And second, couch concept, where you have a massive amount of RAM, and your storage latency becomes less of an issue.
We did cover that. Hang on just a second. Got to go way back. Almost there. Almost. There we go. There's your massive RAM and low latency covered right there. When you suddenly go off cache and everything just completely screws the pooch, that's what this slide was about. Yeah, if you've got a huge cache and you're running out of cache, and that's awesome, now you're dealing with the latency on your RAM until you're not. And as far as offline storage, that's just out of scope. I'm talking about so much stuff tonight, we're not going to dig into tapes.
Because this has been bothering me a little bit, but going back to IOPS, just the definition, you talked about how aggregating them could help speed up or reduce the number of IOPS.
Yes.
But it's still having to write those blocks, even if it's compiling them, isn't it still going to have to write them out and move the arms within the drive? I mean, I don't
Probably
see
not. So if you have a policy that's delaying writes in order to be able to aggregate and coalesce them, then rather than writing one block here and then you've written that block and now you're maybe going to have to move the head over here to read a block over there and then do that over there, the write aggregation and coalescing is going to wait for maybe, hopefully you'll have a quieter spot when nobody's asking for a ton of reads like right now. And then rather than an opt to write that block and an opt to write that block and an opt to write that block, you can do one big opt that writes all the blocks in one strike. So you've limited the amount of operations that you're having to actually feed through your controller to the metal. Does that answer your question?
So there's I'll just point out one other thing. When you're measuring, you can aggregate and get IOPS, but you cannot aggregate and get latency. Latency is another killer.
It's the other way around.
That's where Flash actually comes in to be the big winner.
Yeah.
Because Flash is so much better at latency than any kind of hard drive.
Yeah, aggregation hurts latency, it doesn't improve it for the thing that you're aggregating. Now with that said, if you're aggregating your writes, you're actually worsening your latency to get those writes committed to disk, but you are decreasing latency for reads off the same media because you can use all your operations for the reads rather than having to, mix it up in between lots of little writes and the reads. So, all right.
Question.
Yes.
Drobo was mentioned. How is Drobo structured?
I forget, it's garbage. I forget exactly. It comes up fairly frequently. It boils down to Drobo is a type of JBOD, and it doesn't perform worth a crap, and its resiliency is crap, and it doesn't do checksumming, and it doesn't do a million other things that the cool thing that we're about to talk about does. So I'm just going to leave it at Drobo's garbage. All right. ZFS. ZFS is amazing. If you have never used it, you should use ZFS. There's no substitute, at least not in the open source world. So ZFS, but before we actually get into the Z-pool thing and talk about its topology, has everybody here at least heard of ZFS? Ooh, okay. For those of you who haven't heard of ZFS, and maybe those who have heard it, that's about all you know is the file system called ZFS. ZFS does a lot of things that other file systems don't do. For one, every single block of data written onto a ZFS file system is cryptographically strongly checksummed. Yes?
Does it stand for anything? What does ZFS stand for?
Zettabyte file system originally, but that's no longer true. It is now just the Z file system. It was originally called Zettabyte file system because when it was developed at Sun before the Oracle purchase under Scott McNeely's watch, one of the things about ZFS is it was designed to be able to store a greater amount of data than we thought that the entire human race would ever need to be able to store, the zettabyte. The claim was made that if you populated a maximally sized Z pool which, I mean, you couldn't even build one of those with modern technology. But the idea is, if you populated a maximally sized Z pool with data, the laws of physics would require, I'm not just talking about based on how much energy a hard drive takes, I'm talking about the maximally efficient possible way according to the laws of physics. You would need enough energy to boil every ocean on the planet to flip all the bits in a maximally populated Z pool. That was the concept. And the whole point behind that was, if you go back through the history of file systems, it's just full of stuff that was good enough for now, and then you outgrow it, and it's painful. Because now you've got, a 2 terabyte disk, and you're running an ext2 file system that, won't let you address the whole thing, and now you got to change everything. So that one of the great things about ZFS was this idea that, no, we're going to build a file system that will stand the test of time. Moving back to the thing I was talking about, so every single block of it is checksummed. It's not an error-correcting checksum, like with RAID, which is very simple and can be defeated. You can have collisions very easily. It's a cryptographic checksum. And what that does is allows ZFS to compare the checksum for a block with the actual block and say, this data is good, or no, this data is garbage. I know it's kind of not really the thing anymore, but any of you have a big MP3 collection from back in the day? Anybody want to admit to it? Ever listen to one of those MP3s that you had for years and you hear like, in the second of it, you're like, that wasn't always there, was it? No? No? Never heard a chirp in an MP3?
Oh, yeah.
Your MP3 collection is small. So that's one of the more obvious things that you can see when you have a bit rot problem, where at some point over the years, this file has been in your custody and a bit in it has flipped from 0 to 1 or to 0 somewhere. In some types of storage, it can be really easy to miss that. Like in a simple bitmap, like in the Windows world, a BMP file like you used to have for your wallpaper back in the Windows 95 days, it's really hard to catch bit flip in there, because basically all that's going to mean is one pixel is a very slightly different color than it was to start off with. You won't see it. But in highly compressed file formats like MP3s or like AVIs or MPEGs, a single bit flip can have a pretty massive impact on that image. Like with a JPEG, if you flip one bit in a JPEG, it can be enough to discolor half of the image if you flip the wrong bit. MP3 files, a bit flip will frequently produce a really bright treble just in the second of it. You'll be like, wait, did I hear that? You back it up, and sure enough, it was there. Movie files, frequently you'll get like a bright green, like block kind of flicker, up in one corner, and it'll go away. All this is the result of bit rot. Some of that data has been corrupted at some point. ZFS protects you from that. If you have stored data on a ZFS file system and some of it gets corrupt, whether it's literally cosmic rays flipping a bit on your hard drive, and yes, that really is a thing, it really does happen. When you read that back, it won't match its checksum anymore. If you only have a single disk, then ZFS is going to be like, hey dude, your data's corrupt. Sorry about that. But it can't really do anything because you only had one disk. Hopefully you got a backup. Hopefully your backup's not corrupt. But if you had redundant storage in your ZFS, now ZFS is going to say, all right, this block is corrupt. Well, let me try this block over here from the same data. Does that one match its checksum? Yes, it does. Awesome. Here's your data, and here's me correcting the corrupt copy of data over there, and you go right on trucking. This is amazing. I have personally seen storage systems with tens of thousands of checksum errors still working. And then you have to replace the disk that is just corrupting almost everything that you write at it. But in the meantime, you had no downtime. You had no data loss. Everything just freaking worked, and it's great. All right. That's one thing that ZFS does. ZFS is also a volume manager as well as a file system, where before with the RAID stuff, usually you're looking at, so you've got your disk, you've got your file system, but in the middle you've got a RAID controller with its software or hardware, and so you put your disks in, and you connect those up hardware-wise, and you take your RAID controller and you say, I want to make a RAID 10 array out of this, and do all the thing, and okay, now it's a RAID 10 array, and now I take my file system and I format that, and now I put all my files on it. With ZFS, you just plug in all the disks, you don't need a separate controller, and you say zpool, create, yada, 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 and poof, everything is magically there. It's got your data set up the way that you wanted it to. It's checksummed everything. It can automatically heal it if you got corruption. ZFS can also replicate this stuff from machine to machine, which might not sound like a big deal. Who here knows about rsync? I better see a lot of hands go up. Fabulous. Have you ever tried to rsync a 1 terabyte file? How'd that go for you? All right, so yeah, well, so the issue with rsync, the first time you rsync data from A to B, there's no magic in it. It has to copy every single block from A to B, as anything does. But the promise of rsync is that the second time you synchronize this data, it will look on both sides and see, okay, what pieces of this data have actually changed. And then it only has to move that data across the wire, which is amazing when you've got fast storage and like a dial-up internet connection, because now you only changed 10K of data and you'll have to move 10K over the wire, and it's great. But when you've got, like, for instance, virtual machine images that may be multiple terabytes in a single file, the only way rsync can tell what data has changed is to read every single block of that multiple terabyte file on both systems, create a list of these blocks with checksums, send the list of checksums over, compare all those checksums to see if any of them are different. Then it actually has to do it all over again for the ones that didn't match, because those were really weak checksums the first time, and now it has to do it again with stronger ones. Then once it's done all that, now it can move blocks across the wire. When you got a multiple terabyte file that you only changed 10 meg worth of data on, that 10 meg might go over the wire in a couple of seconds, but it might take you hours to read that data from the storage on both sides. And worse, while you're doing it, remember, IOPS, you are saturating your disk systems on both sides for IOPS, and everything is slow as dirt while that's going on, so it won't work. Now what's different with ZFS replication is with ZFS you take snapshots, which I probably should have already talked about. Matter of fact, diversion. ZFS you can have snapshots. If I say ZFS snapshot data at snapshot name, I've just preserved every single block of that data as it was at that point in time for all time. It takes absolutely no time to complete. If I ever want to go back to that state, ZFS rollback data at snapshot name, instantaneously. Doesn't matter if terabytes worth of data have changed, instantly it goes back to where it was. Much better than I can snap my fingers.
I can't snap my fingers.
Yeah, so the other thing about these snapshots, you can have hundreds or thousands of these snapshots that all represent points in time in your file system. They're all recoverable. You can inspect them individually. So unfortunately, although Apple trademarked the idea with storage, it's like a real-time machine, not like the fake crap that Apple does, which is file-based and horrible. Everything with the snapshots on ZFS is block level. So absolutely everything at that moment is preserved. Now the cool thing about that is ZFS replication works with these snapshots. You don't actually replicate the file system, you replicate the snapshots. So you start out, you've got a 10 terabyte file over here on this system, right? You say ZFS snapshot 10 terabyte file at 1, because you're not very creative. So now you have snapshot number 1. You say ZFS send snapshot 1 to this machine over here, over an SSH pipe. So there's nothing magic here. 10 terabytes of data has to flow from A to B, right? Nothing special. But now, you change 10 megs worth of data on this 1 terabyte file over here on machine A, and now you say ZFS snapshot 10 terabytes at 2. And you say ZFS send -I for incremental at 1 at 2 over there to the machine to the other one. Now it already knows you have snapshot 1 on this machine and on that machine. And what that snapshot actually is a linked list of all the blocks of that file system at that point in time. So it already knows, because it has these 2 snapshots that are really just linked lists of blocks, it knows which ones have diverged in 2. It doesn't have to read all this data to compare to C. It already knows. So when you say do this incremental send from A to B, it immediately flings those 10 megs across the wire. It doesn't have to grovel over the storage first. So ZFS replication is amazing. Anyway, all this crap is why you should use ZFS. Now let's talk about how the storage actually works. The base unit is a Z-pool. Z-pool is a JBOD of VDEVs. So the VDEVs each consist of one or more physical disks. A VDEV is a lot like those classic RAID arrays types that we just went through in the first half hour or so. Make that the first hour or so, because this is taking a while. So specifically, and this is one of those things that everybody gets wrong, and it doesn't help that the actual ZFS developers are sloppy and frequently incorrect when they talk about this. The ZFS devs will usually say that Z-pool is a stripe. They're lying. It's actually a block level, semi-round robin, ordered by free space available JBOD, which fills all VDEVs at the same relative rate. Now what that means is, if you have a 1 terabyte disk, a 2 terabyte disk, and a 4 terabyte disk, and you put all those in a Z-pool, this is sort of like the RAID 0 that we were talking about before, but the difference here is that it's a JBOD, and it will fill those disks up according to how much space they have free. So we had a 4T and a 2T and a 1T, right? So you're going to write 4 times as many blocks to the 4T disk as you do to the 1T disk. And you're going to write twice as many blocks to that 4T disk as you did to the 2T disk. So they're all filling up the same relative rate, and they will all fill to 100% at exactly the same time. That's the way that ZFS actually fills the pool. There are some other little things that can happen that can influence its decisions for any one particular block write, but if you go online and you look this stuff up and you start asking people questions, you absolutely will be told completely wrong things like, oh, ZFS is amazing, it writes to the least busy disk so everything is as fast as it can possibly be. No, it doesn't. If you put an SSD and a rust disk in the same pool, you will bind on the performance of that rust disk. It will be as slow as that rust disk. The SSD will not make it all go fast. All right. There is no fault tolerance at the Z pool level. When I said if you put a 1T disk and a 2T disk and a 4T disk into a pool, there is no fault tolerance. If you lose one of those disks, you have lost the whole pool. You haven't lost the data on that disk, but you have the other two. You've lost the pool. It's all gone. You're fired. Okay, there's no significant loss of storage efficiency or performance at the Z pool level. It trends towards all the storage and all the IOPS. You don't really lose anything at all there. It's just everything glommed together. So that's the plus side of not having any resilience or fault tolerance. Now let's talk about those VDEV types. Remember I said each VDEV, it can be anything from a single disk to something resembling a lot of those classical RAID array structures that we talked about before. Other than this single disk, which you should never do because, again, you'll lose all your data and get fired, the simplest topology for a VDEV is a simple mirror. It's just like a RAID 1. You write all the blocks on this one and on that one. So you've got 1D worth of storage efficiency, 1D worth of write IOPS, and ND, so 2 if you got 2-disk mirror, 3 if you got a 3-disk mirror, worth of read IOPS. I wrote it right this time, if you ever caught me on the last one. Okay.
It was on the bottom instead of
So what now?
It was on the bottom. The read was on the bottom instead of the top left.
Okay, so for storage efficiency, again, it's just like RAID 1. You've got the storage efficiency of, well, now we're talking about a pool of mirrors. We're not just talking about one single mirror VDEV, we're talking about a pool of mirrors. And I was very careful not to say ZFS RAID 10 here. The reason I was very careful not to say that is it's not RAID 10. If you see somebody online say ZFS RAID 10, they're referring to a pool of mirrors and they're doing it wrong. There's a lot of things about RAID 10 that do not apply here, and calling it ZFS RAID 10 just encourages people to not understand what's actually going on in their storage. Everything is a pool. You have VDEVs in it. If you have a pool that has all mirrors, it's a pool of mirrors. In some ways, it's like a RAID 10 in the storage efficiency and yada, yada, yada. But so here we have, instead of ND, we've got VD. So V is the number of VDEVs you have in your pool. So you have your number of VDEVs worth of storage efficiency, worth of write IOPS, and you actually have the number of VDEVs times the number of disks in each VDEV worth of read IOPS. Because again, you can read a block out of any single one disk. You don't have to light it any extra ones up.
Each pool has the same topology?
Yes, there's only one topology for a pool. It's that semi-round robin JBOD that fills up, you know, at the rate of available space on each VDEV event.
Right, but what I'm asking is that you have to, all the mirrors have to match?
No, no. There's no relation between VDEVs. You can have one pool with one single disk, one 2-disk mirror VDEV, one 19-disk mirror VDEV, one 8-disk RAID Z1, and 3 4-disk RAID Z2s, because why not? And you can put them all in a pool. It's a bad idea and you shouldn't do that, but you can't. So there's only one topology for the pool, and each VDEV can be whatever the heck it wants to be.
Gotcha.
So can ZFS actually do the mirroring itself, or do you have to have?
ZFS does everything itself.
Okay, so you don't. You can actually just use the JBOD with the disks and not have.
You do not want to have a hardware RAID controller at all
Okay.
under ZFS.
Okay.
If you have one, you want to figure out if you can flash it into, what do they call it? You want it to just act as a host bus controller.
A lot of them you can actually just spool by tying each individual disk as a.
No, don't do that. Yes, you can do that. It's a bad idea. Don't do that. You want to find out if it can be flashed to. Does anybody know that? What's the name of the mode that you can flash like some of the LSA controllers to just make them a host bus adapter? Does anybody remember? It's like on the tip of my tongue.
I had a question.
Yeah.
In the case that you set up like that there, it kind of follows from on the question over there. When you're doing the mirrors, in that case, would you be constrained as far as the size of the smallest VDEV in that group of mirrors?
Only in the sense that if you've got, let's just say, let's make it simple. You say you got a 1T mirror VDEV and you got a 2T mirror VDEV in the same pool. ZFS is perfectly fine with that, doesn't care. It's going to fill them up at the same relative rate so that they will both reach 100% full at the same time. Now, performance-wise, this means you're going to write twice to this 2 terabyte VDEV for every one write to this one over here. So you're basically going to end up, you're going to be binding on half the available performance of this VDEV. Whereas if you had the exact same size VDEV with the same amount free, they fill up the same rate, and now you're basically, you know, binding on each one of those put together at full performance. You'll have, you'll bind either on half the performance of that VDEV, or in a more ideal situation on half the performance of that plus the full performance of this one. So it won't perform as well.
Now, you've got the 1 and the 2.
Mhm.
Are they each a pair?
Yes.
Okay.
Because we said they were. They don't have to be. I mean, this one could be a 1 terabyte single disk, and that would be a 2 terabyte mirror. But if you lose that single disk over here, you lost everything, including what was on the mirror.
Right, it's not just that the 2 of them are a mirror of each other, it's
No.
that they are each
No.
a mirror.
At the pool level, nothing is mirrored between, there is no fault tolerance between VDEVs.
So the mirror VDEV mechanism is the only real protection you've got.
It's inside the VDEV.
Yep.
VDEVs can be resilient. Pools are not. They are only as resilient as their individual VDEVs. If you lose a VDEV, you lose the pool. So do not use non-resilient VDEVs. All right. So yeah, we can survive any single failure. Each individual VDEV in a pool of mirrors, it's a mirror. It can survive any number of failures as long as one disk remains. As far as the whole pool is concerned, you can survive any number of failures as long as each VDEV has one remaining disk. The minute any one of those VDEVs loses all disks, the whole pool's gone. And calculating the odds on that is exactly like calculating them on RAID 10. All right, RAID Z 1, 2, and 3. These are pretty easy, and I don't get as upset if somebody says ZFS RAID 5 or ZFS RAID 6, because it's, now we're only comparing the VDEV to the RAID array, and it's a pretty good comparison. I get upset about people saying ZFS RAID 10 because it's a pool, it's not one single VDEV. But now we are just talking about a VDEV with a RAID Z 1, 2, or 3 array. RAID Z1 is like RAID 5. RAID Z2 is like a RAID 6. If there were a RAID 7, that's what RAID Z3 would be. So it's a stripe with single, dual, or triple parity. So your storage efficiency is exactly what you'd think it is with these. If it's a RAID Z1, then it's all your disks less 1. If it's a RAID Z2, all your disks less 2. You can do the math on the other one. So for the IOPS, again, just like the RAID 5 or RAID 6, you're trending to a single disk worth of write or read IOPS. But it's actually not quite that bad because things get kind of weird with ZFS, and we'll cover that later. Like in this slide right here, RAID Z has variables with stripe writes. So what that means is, in a RAID 5 array, if you want to write a single block to an 8-disk array, you have to light up all 8 disks. Worse, if that particular stripe was already partially full, then you're going to have to read all 8 disks to get the original stripe in memory. Now you're going to have to insert your block that replaces some other block, recalculate your parity, and then write all 8 blocks right back out to the disk. So you had to light up all of the disks in the array, not only once but twice, to get your one single block written out. RAID Z is a little smarter than that. It can do a variable stripe width, which means that if you're only going to write one block, for a RAID Z1, you only have to light up 2 disks. One for the data block and one for your 1 disk worth of parity on it. So if you've got, let's say that you've got a 6-disk wide RAID Z1 VDEV, and you want to write 3 individual blocks, but they're not all in the same stripe, you can actually, if you're lucky, you can do all of those at once, because you can write to disks 0 and 1 for the first block, and write to disks 2 and 3 for the second one, and write to disks 4 and 5 for the third one, so you get all 3 of those things happening at once. So you've tripled your IOPS, which is amazing. Now, it won't actually always work that way, because what if you need to do a full stripe read over here, a full stripe write over there? You're still going to bind all disks on that, but it helps. So RAID Z isn't quite as bad as traditional RAID for stripes.
Next time you write that, say you should make the last one 3, not 2.
Yeah.
Copy paste.
Oh, yeah, RAID Z3, yeah. Writing one block to make disk RAID Z3 will have to write to 4 disks, because the one data and your 3 parity.
You're gonna talk about the RAID write hole?
Yeah, so I actually already described the RAID write hole. What that refers to is what I was talking about, where you only want to rewrite a single block of data onto a RAID stripe. But it's an already populated stripe, and you say, okay, I want to replace this block right here, or maybe even this block was empty and I want to fill it. You end up having to read the whole thing in and then fill that hole and recalculate your parity and then write the whole thing back out again. So it's just a huge performance suck. If you have to do many of those, and it's awful, because instead of doing one op to write that one block, you've got to do, for an 8-disk array, you're actually doing 16 ops, because you're having to read one block off of each one of those disks and then recalculate your parity and then write every one of them right back out again.
Data corruption issue, you crash in the middle of that process somewhere.
Yes, the whole stripe will be bad. What the actual impact of that is going to differ between file systems and between RAID controllers. If you have a relatively smart RAID controller, like say Linux MD kernel RAID, it's actually not going to commit that stripe until all the blocks are written. So what you actually end up with is you're missing the whole stripe rather than having a corrupt stripe, which is what you really, really don't want. Yes?
Does ZFS actually read each block and fill it, as in a partially filled block, and then fill the empty space, and then cryptographically sign it or checksum it and put it back? Or does it just grab an empty block and put the new data there?
It grabs, so if we're only talking about RAID Z1 right now. 2 and 3 are the same thing, just add an extra block or an extra 2 blocks. Assuming a RAID Z1, you'll actually write 2 blocks, because you've got to write the data and you've got to write its parity, which in this case, because it's only 2 blocks, it's effectively, it's redundant. They're both the same. So yeah, you're going to write 2, but that's still a big improvement, where if you had an 8-disk stripe, you're not lighting up all 8 disks.
Yeah, I'm more getting at that you've got a partially filled block. You're not going to read that into RAM, add data to it, and then write out that partially filled block, or now full block, back to the same spot. You're going to be writing it to a new
Yeah, well, so ZFS is a copy on write file system. You don't ever actually overwrite data that's still live. You can only ever write to space that has been discarded. So yeah.
Question?
Yes.
Are the disks synchronized in these setups?
I'm sorry?
Are the platters synchronized, the same, their orientation all the same in these setups?
I think you're going a few levels too deep here.
Just a bunch of disks.
Yeah, it's just a bunch of disks.
All right.
I mean, there may not even be platters. There may not be, hard disks at all. There might be flash. It might be a mixture if you're not too bright. Some of them might be local. Some of them might be over network. I mean, all that's way underneath the spec.
Yep.
This is not the inside of a hard drive we're talking about. All right. So the thing that a lot of people forget when they look at RAID Z is they just want to say, oh, okay, so RAID Z. I put all my disks in this big RAID Z. I've got a 24-bay system, so I put 24 disks in a RAID Z1 or a RAID Z2. Awesome. No, not awesome. Yes, you can do that. It's a bad idea. It's a pool. It's always a pool. Even if you only have one VDEV, it's a pool, but you should never have a VDEV that's 24 freaking disks wide. Keeping in mind that the IOPS of any pool is going to trend towards the number of VDEVs with the write ops and the number of VDEVs with the read IOPS. That means that you should, even if you're going to do RAID Z1 or RAID Z2 VDEVs, you should have a pool of them if you've got lots and lots of disks. So let's say you've got a 24-bay system and you want to fill it up. You might, for example, say, well, I want to do 6-disk RAID Z1 VDEVs and I can have 4 of them. So now those will perform. The naive thing to say is it will perform 4 times as fast as if you put them all in one big 24-disk wide VDEV. That's absolutely a true statement, but it doesn't go far enough, because the wider you make that VDEV, the worse it's going to get. So you not only have 4 times as many VDEVs, they're also not as sucky VDEVs in the first place. You'll also have greater resiliency. Now, you will lose some storage efficiency, where if you said, I want a 24 disk wide RAID Z2, I've only given up 2 disks worth of storage efficiency to parity, right? Whereas if you did 4 6-disk RAID Z2s, well, now you've given up 8 disks to parity instead of 2, but it's a good idea. Your rebuilds will be tremendously faster when you lose a disk. In the 24 bays, you're going to lose some disks. It also means instead of only being able to survive 2 disk failures, you can now survive up to, let's see, we've got 4 VIDAs, you can survive up to 4? Yeah, up to 8. You can survive up to 8 disk failures in this, because you can lose up to 2 disks in each VDAV. So yeah, if you got a lot of disks, you need to have a pool, not just one VDAV, and that's how it's going to work. No matter what the VDAV type is, you're going to have that many VDAVs worth of write IOPS, that many VDAVs worth of read IOPS. Yeah. So again, you'll survive as long as all your VDAVs survive. If you lose any VDAV, you'll lose the entire pool. And like I just said, beware the widely striped VDAV. You'll see people, if you go to places like, Reddit, rFreeNAS, or rdatahoarder, you'll see all these people who have gone out and spent thousands of dollars on 24-bay systems, and they have dumped them all into a single VDAV, and frequently they have very rapidly lost data, so don't do that. It's not the fault of ZFS, it's the fault of the sysadmin for building a really, really silly system. So some real-world recommendations. RAID Z1, you should almost never use RAID Z1 for the same reasons that you really shouldn't use RAID 5. Can anybody tell me why you should never use RAID 5? Anyone? No takers? You don't use RAID 5 because it takes too long to rebuild a disk. Modern disks are no longer little tiny things that you can read the whole thing in an hour or so. If you've got like,
All day.
Yeah, all day. So
you rebuild half the drive and then another drive fails.
Exactly. So you got a RAID 5 array. You got an 8-disk RAID 5 array, and it's 8 terabyte disks, and it's going to take you, basically all day long, maybe worse, to rebuild that array. In the meantime, you're absolutely lighting up the rest of your disks as hard as you possibly can, and you bought them all at the same time. And this one just already died. Odds are really good you're going to burn another one while you're trying to rebuild. And if you haven't succeeded in rebuilding your replaced drive, you just lost everything.
You're off by a factor of about 500.
Yeah.
I'm
Yeah.
serious.
Yes.
I
Yes.
did work.
Yes.
I did work.
No argument whatsoever. It can absolutely be way, way worse than that. You're completely correct. Yeah, a lot of people have seen, like with ZFS, like if you rebuild an 8-disk RAID Z1 ZFS with 8 terabyte drives, you shouldn't be seeing weeks. You should be able to get that done in a day or two. But conventional RAID 5 and a system that big, yeah, it can take hideous amounts of time because you're usually on your rebuild. You're gonna bind on IOPS, not throughput. Remember, we looked at the difference between 200 megabytes a second and like 0.2. That's the speed you're gonna be filling that drive at. And that also means you're doing the maximal amount of work on all those other disks, which again, if one of those fails during that process, you're done.
Plus you have normal production on it.
Yeah.
Sharing it, right?
Yeah.
And you're killing
Your
performance
your
of
production
something
just
that's already
moves
slow.
through the through the floor.
Well, actually, some systems won't. Some systems will save production maintenance and then last longer.
Yeah, you can't have both. All right, so real world recommendations. A lot of people say you should never use RAID Z1. They're wrong, but no more than 3 disks, please. A 3-disk RAID Z1 is a pretty reasonable compromise between a pool of 2-disk mirrors. When you're like, I want pretty close to that level of performance, but 50% won't quite cut it for me for storage efficiency. I want 66.7% worth of storage efficiency. 3-disk RAID Z1 VDAVs are perfectly freaking reasonable. That's fine, but please no wider than that. RAID Z2 and RAID Z3, I don't have a whole lot of use for RAID Z3. Honestly, RAID Z3 encourages people to build stupid wide VDAVs, and the operative word is they're still stupid. I don't recommend more than 12 disks in any one individual VDAV, whether you're doing RAID Z2 or RAID Z3. You're spreading things out too far and asking for too much trouble otherwise. And usually, I wouldn't go that wide either. You better know what you're doing if you're building 12 disk wide VDAVs.
So can you build a zettabyte ZFS?
With unobtainium hardware that we don't possess,
Okay,
sure.
but no, I mean, you say never go bigger than 12 disks on a RAID Z2 or Z3.
I didn't tell you how many VDEVs you could have in a pool, or how big each one of those VDEVs could be in terms of storage space.
So let me ask the question again. So can you build a ZFS drive with configuration?
With unobtainium hardware that doesn't exist today, yes. I mean, if you're going to build that, it would require so much power by the laws of physics, not by our current technology, that you would boil all the oceans on the planet when you flipped all the bits from 0 to 1. So, no, we can't build that right now. The logical ability is there. The file system scales that far. Our hardware does not. All right. And then there's butter. So, start out with butter RAID 1. Butter RAID 1 isn't RAID 1. It will break your freaking head trying to figure out how it's RAID 1 because it isn't. The really cool thing about butter RAID 1 is that, let's say that you're a home user and you've got like all this crap that you've been scrounging in disk drawers over the years. You're like, I found a 500 gig drive over here, and I got a 2 terabyte here, and I've got like, this weird 720 that I brought home from, Dad's work over there, and I've got this 4 terabyte disk here. I just want to like glom them all together into one big storage thing. It's a thing that a lot of people want, and butter RAID 1 will do that. It will not only do that, it will actually give you redundancy amongst that odd-numbered, mismatched pile of mutts that has nothing to do with each other. The reason it does that is because it's not mirroring drives at all, which you'll recall is what RAID 1 did. What butter RAID 1 does is it just says, I'm going to, each time you ask me to write a block, I'm going to write it to 2 separate drives. It doesn't matter which one of those 2 drives are. It won't always be the same 2, but it'll go to 2 different places. So you can lose any one of these drives out of this butter RAID 1 and not lose any data because you have another copy of those blocks somewhere else in this monstrosity of a thing that you built. I was really excited about butter when it came out. If you go trolling through, that collection of slide decks, you'll find some from 5 years ago where I was like, butter is awesome. It's going to be the jam. It'll kick ZFS's butt. Give it time. I was wrong. So in theory, butter RAID 1 will survive any single disk loss. In reality, it will probably just eat all your data before you lose any disks. Butter is not stable. It's not going to be stable. Don't rely on butter. Butter RAID 10 is also not RAID 10. Like RAID 10, it does require identically sized devices in pairs, but its distribution is still funky, and I've frankly forgotten how it worked. I used to know when I was a fan of butter, but it's been years and I've kind of forgotten. And right now, the recommendation is literally just not to use it because it performs worse than butter RAID 1, and you can do butter RAID 1 on the same set of disks and have the same redundancy, so just do butter RAID 1, yay. If that all sounds kind of weird, like, okay, well, why do you have this thing then if it sucks and it's not any better than the other thing and it doesn't do any things the others did? Why is it still there? Welcome to butter. Let's see here. There we go. Butter RAID 5 and RAID 6 has been coming. And like the next version, just wait a couple of months, guys, for like, I think it's, is it 7 years yet? 6 or 7 years. It is still not ready. Even the butter developers who are insane enough to tell you that you should use butter will tell you don't ever use butter RAID 5 or RAID 6 under any circumstances. It's not production ready. They're not kidding.
Put the foot gun right there.
Yeah. I mean, yeah, that's what I'm telling you. It won't survive all the disks being online, let alone if you lose one. And I'm really, really not kidding about that. Let's talk about some of the ways that you can increase your chances of losing data on butter. Now, this actually comes from the Debian wiki. Now,
can we just rename this file system Banana Peel?
Debian is not exactly the most hot-headed, accusation-flinging, organization out there. They tend to be thought of as pretty stable. They are also incredibly FOSS-friendly. They love the GPL to the point that they forked Firefox and renamed it Ice Weasel so they could get the trademark mascot out of it. So these are the exact folks you would think would be saying, yes, we're going to promote butter because it's GPL and we love it. It's not that total crap that we can't get in the kernel. But on Butter's page in Debian's wiki, they have a section on warnings that is basically, these are things that they have figured out are more likely to make you lose data on Butter. That includes using any underlying block level clones, like with LVM. Other unspecified LVM interactions, they are pretty sure will make it more likely that Butter will eat your data. If you use solid state disks with kernels before 4.14, there's a special mount option that you should use to lie to the system and say this is not a solid state disk, because the solid state disk optimizations will eat your data. If you mount a 2-disk RAID 1 degraded twice, it will be read-only forever. It's not repairable. So the whole point of a 2-disk RAID 1 is you can lose a disk, right? Well, if you do that, don't mount it. You can get away with it once. If you do it twice, you'll never ever write to it again. Welcome to Butter. Trying to use Butter compression. One of the features that I didn't mention that ZFS has that is amazing is inline compression. You can turn on gzip compression or LZ4 compression, or now there's a couple of new types out. It'll automatically compress your data as it's written to the disk, increasing both performance and storage efficiency, and it's amazing, and nobody's ever lost a byte of data because of it. Butter, on the other hand, if you turn on Butter's compression, it will eat your data, especially LZO, but anything to some degree. And none of this is a guarantee. It's not as simple just like, oh, I turned that on and the next day, you know, it was dead, guaranteed. This just makes it more likely that something bad will happen. There's also no guarantee that if you don't do any of these things, bad things won't happen, because I ran Butter in production for a little while and did none of those things and lost everything. Using the Butter auto defrag mount option, which you would think, well, of course I want that. I don't want my data fragmented. Data fragmentation is bad. Unfortunately, Butter will eat your data. And many, many more. You can look at lots more of them if you go to Debian's wiki. And this is just, you know, like I said, this is in the warning section, and it's stuff that, you know, we are certain at this point that this makes it more likely that Butter will eat your stuff. So, yeah. Hopefully you've gotten the impression. Please don't use Butter. Now, with that said, some of you may be out there grumbling and saying, well, SUSE is using Butter as its default file system. It can't be that bad. And Synology is formatting its NASs with Butter, so it can't be that bad. Here's the trick. In both cases of OpenSUSE using Butter as a default file system, and in the case of Synology using Butter on their NAS devices, start off with Synology, because obviously it's a NAS. You got multiple disks, right? So of course you would want Butter to have access to all these disks. So, you know, it does the block level checksumming just like ZFS does. So in theory, it'll keep your data from dying. Well, you have to feed it all the disks individually so that it can distribute the data among them, and it has some place to recover the data from if the data gets corrupted, as it can tell by checking the checksum didn't match, right? Wrong. Synology uses LVM underneath it and feeds the whole thing to Butter as, I'm sorry, not LVM, uses MD, Linux kernel RAID, to build a kernel RAID 5 and feeds that to Butter as a single disk with none of the damn features turned on. That is how Synology uses Butter. And that is why your Synology NAS is much less likely to eat your data. Also, you can't fiddle any of this stuff with the Synology NAS. You've got like the one magical blessed configuration with absolutely none of the features turned on that would make you want to use Butter in the first place, and that probably won't lose your data. So like, you know, if you just had Butter like on a single drive in your laptop and you didn't turn on any of the fun features, it probably wouldn't eat your data. It's kind of where we are. Does anybody have any questions about Butter?
Should we use it?
Why?
So what now?
Why?
Why what? Why does Butter exist?
Is it an exercise? I mean, is it a...
No, where did they go wrong, actually? Because you said
Yeah.
they really
The thing is that he wanted ZFS, but the licensing wouldn't let them use it in the kernel.
The problem with ZFS is ZFS is licensed with a very uncommon open source license called Cuddle. Common something development license. The Cuddle was originated with Sun back in the day when Scott McNeely owned the place, and there is no incontrovertible proof of this, but the odds seem very good that Scott McNeely developed the Cuddle license specifically to have an open source license that would prevent his crap from getting used with Linux. Because Scott McNeely, and this part is not a rumor, he will tell you himself, he absolutely hates Linux. I have seen this man get up in front of it on a stage in front of 1,000 people and talk about how the entire open source world was just going to go into flames now because Scott McNeely had retired and they didn't have Scott McNeely stand up for him anymore, and all they had was this Linux crap. So, yeah. the promise, the big promise of Butter when it came out, when Chris Mason first started developing it at Oracle. By the way, a lot of people think that Butter is something owned by Oracle. It is not now, and it never was. Chris Mason started developing it while working for Oracle, but it was not an Oracle property. Chris Mason is still the prime developer when he left Oracle, and I think he's working for Facebook now. Development went with him. So no, Oracle doesn't own it, however, it does still suck. But a lot of the promise when he started developing this was that we'll get all these next generation features. We'll get rapid replication, which Butter has, only it doesn't really work. We'll get the blockable checksumming, which does work, but just unfortunately the whole file system tends to die or render and get moved. We'll have the volume management on the inside. We'll have, we'll have the inline compression. We'll have all this great stuff, and we'll have it licensed under the GPL so it can be built right into the kernel. And in fact, right now, Butter is built right into the kernel. So if you want to lose all your data, you do not need to depart the friendly confines of your local Linux kernel to do so. But the problem is that file systems take a lot of expertise, a lot of personnel hours, and a lot of time to develop. It is a long, iterative process requiring one heck of a lot of expertise. And when Butter first emerged, of course it was not that stable. And a lot of people railed at it, and I told those people they needed to wait and give it time. I wasn't wrong. They did. Unfortunately, it's been given time, and it's not getting more stable. I can't tell you on a line-by-line audit of the code, like, okay, this is exactly where Mason and crew went wrong. What I can tell you is they've been going wrong. They keep going wrong. It is not only not any more stable now than it was 5 years ago, it's less stable. So I'm done with Butter.
Is that why it's called Butter?
So btrfs stood for B-tree file system, and some people say B-tree file system, some people say btrfs, some people say btrfs, some people say Butter. I usually say Butter.
No wonder you call it Butter.
Well, people used to make jokes, Butterface and Butter Data.
Yeah.
All right. So I was asked on Twitter about mergerfs and SnapRaid. So we'll talk about mergerfs. Mergerfs is one example of something called a union file system. And union file systems are a file system that basically you save your data just like normal data in a normal file system on disk 1 and on disk 2, but you don't have to manage disk 1 and disk 2. The union file system just kind of squishes them all together, so it looks like one disk. But the cool thing about a union file system is if disk 2 catches on fire and you have to pull it on your machine and throw it in the toilet, so it goes out, all the data that was on disk 1 is still there. You did lose everything on disk 2, it's gone, you're not getting it back, but all the stuff on disk 1 is not only there, it's still mounted, and you can just mount it as a normal disk in the ext4 file system and see the files and the folders that are on there. And all you lost was what was on disk 2. Yay, I guess. So that's what mergerfs is. Now specifically, it's a user mode file system, Fuse, for those of you who played those things before, which means that although you will read lots of things about how great its performance is, they're lies. It performs very well for a union file system, which is a pretty low bar to hurdle. But it runs in user mode, not in kernel mode, and it's not going to be very quick. And that is basically exactly what it's going to do. You're going to feed it disk 1 and disk 2, and you're just going to say, I want to save file 3 in folder 1, and it will decide whether it's actually going to put it on disk 1 or disk 2. If you ever lose one of those disks, then you can ignore the union, and you can literally just look at the remaining disk and see that stuff there. One cool thing about a union file system, it is very simple. It does lend itself well to that kid with the collection of hard drives that none of them match that he's found over the years, that he wants to just cram into one box and have them all online at once and be like, yay, I have X terabytes of storage. It will do that for you, and it will minimize how badly you hurt yourself when one of them inevitably fails. However, you will lose data when it does, which is why I don't get excited about it.
Union file systems seem most useful with Docker.
I'm sorry?
Union file systems seem most useful with Docker. That seems to be the driving force behind union file systems of late.
Can't really speak to that.
Well, you have like a static configuration with an overlay. It's just the overlay, right?
Well, it's Docker. You build one image, and then you use that image to build another image, and you layer these images.
You're doing file system elements, basically.
Yeah. All right. So mergerfs that we just talked about is a frequent underlayment to SnapRaid. SnapRaid is a really, really confusing, really, really popular thing. I had known for quite some time it wasn't something I was interested in because it didn't do, it doesn't do basically any of the things that ZFS does that I love. And it's also just plain weird. But I took the time to actually dive into it and figure out how it actually freaking works as a result of, is the person who tweeted to me asking about SnapRaid and MergerFS, did you show up? Kidding me. Somebody from the TriLUG like tweeted at me, was like, will you talk about MergerFS and SnapRaid? And he's not,
Are they trolling you?
I did.
Oh. Some people left. I don't know.
I did, and I said I would talk about it. And I spent like an hour and a half learning what this thing was, because nobody talks about it, because nobody understands what this crap is. They just install it and say, yay, I have it, and it's awesome, and I love it, you should love it too. All right, so what SnapRaid actually does is, you say you have these 3 disks or 3 file systems, my first disk, my second disk, and my third disk. They're individual disks, they got their own files. There is no union at this level, they're just 3 disks, they just do their thing. You can take a 4th disk and you can tell SnapRaid, this is my parity disk. And you tell SnapRaid, now I want you to do a sync, and SnapRaid will grovel all over your first 3 disks on a file-based level, and it will do this monstrous like parity calculation thing between files that it decides it wants to match up amongst the 3 disks, and store all this parity on the 4th disk. So now if you lose one of those 3 disks, you can reconstruct what was on it from the parity that was saved on the 4th disk and the remainder of the stuff that's on the first 2 disks. Now that only works if you haven't deleted any of the files or modified any of the files on those 2 remaining disks since the last time you ran a SnapRaid sync, which is a dirty operation that takes a long time. It's going to grovel through all your files. That's what SnapRaid is. Now you can combine SnapRaid with MergerFS so that now you don't have to actually manage mount my first disk, mount my second disk, mount my third disk, because MergerFS you still have mount disk 1, disk 2, disk 3. But you also have mount MergerFS that lets you look at them like they're all one. And then you have the 4th disk, and then you have SnapRaid doing its thing there. So at the end of the day, it's not really RAID. It's also not really a backup. SnapRaid's docs frequently say that it's not really RAID, it's more like a backup, but it's not like a backup either. It's sort of the hedge that maybe you won't lose some of your data depending on whether you change your stuff. They will mention in the docs that it's not really appropriate for like databases or boot disks, anywhere where the data is changing very often. What they're not spelling out is it's because if the data has changed since the last time you ran this operation, it may take an hour to run, then you've just lost unspecified hunks of data should you lose one of those disks. So SnapRaid is the kind of thing that like, it's very much a kid in the basement kind of a thing. Like it's better than nothing. You won't lose all your crap, hopefully, if you lose a disk, but
so it's like using rsync as a RAID control.
So it's confusing and useless? That's what it sounds like?
Yes.
If your goal is not to lose any data, SnapRaid is completely useless. If your goal is to lose an unspecified amount less data than you otherwise would have without spending a whole bunch of money on hardware, SnapRaid is useful.
So what you're telling me is that nobody should use it because nobody wants to lose data.
Some people,
John,
pretty much.
some people don't care.
Pretty much.
Yeah, well, those people can go and build junk.
All right.
I don't want junk.
I have a feeling that some of you were still kind of maybe seething a little bit when I was talking about how horribly, the stripe topologies performed. So I made some pretty pictures to demonstrate what I was talking about. For any of you who weren't familiar with that. All right, so we can see here, this is idealized throughput on an 8-disk RAID Z2 VDIV. And now we're looking at RAID Z2 here, but it's no different than RAID 6 would be. And if you just assumed one less block of parity, make a 7-disk, it's the same as a RAID 5 would be. This is idealized. So we say if we want to read 6 blocks worth of data, we light up our 8 disks to do so. It all happens in one operation. It's nice and quick. That is 6 times as fast as if those blocks were all stored on one disk, right? Now we look at throughput versus IOPS. This is what happens when that data isn't all on one stripe. You've got to light up all these 6 different stripes, and each time you have to light up every single disk in the array to read each one of those stripes. So you're actually only performing as fast as you would if you only had one disk. Now RAID 10, or a pool of mirrors, is a whole freaking different story. Now we're looking at how long it takes us to read or write 8 blocks. And you'll notice that We're lighting up half the number of disks for reads that we do for writes because, again, we can pull off of either disk that we want to. So you've actually got 8 disks worth of IOPS here, and you've got 4 disks worth of IOPS there. And again, being that we're mostly talking about ZFS because I love it, you should too, the big lesson I want to drive home is regardless of what type of VDEV you're using, more VDEVs in your pool means more performance. IOPS tracks VDEVs. So over here we have a single 8-disk RAID Z2 VDEV, and as you can see, in our worst case, we've only got 1 disk worth of performance. Now we look at the same 8 disks configured in as 4 2-disk mirror VDEVs in one pool, and you can see how much less frequently they have to light up than the other. For read performance, we have 8 times the performance. This is 8 times less utilized than the Stripe. For writes, we have 4 times as much performance. It is only lighting up twice for every 8 times this one lights up. This is why I keep saying more VDEVs, more VDEVs, more VDEVs. Yes, it is theoretically possible that your one big wide VDEV will perform really well. We look at that right there. Well, I'm a little laggy going through these GIFs. So we look at that right there. It can look like that. It's possible for it to look like that. It's very, very rarely in practice going to look anything like that. All right. All right. So the IOPS of any VDEV tracks its slowest disk. We covered that. Resilvering, which means when you have a disk fail and you replace it, your resilver performance, it's going to track IOPS, not throughput. So you should be expecting pretty much your worst case scenario. If you're resilvering a disk on your RAID Z1 or RAID Z2 array, you should expect it to perform like a single disk would perform when you're absolutely hammering the dog crap out of it, because that's exactly what you're going to be doing.
What is resilvering?
Resilvering is when you're rebuilding that disk. You replace the failed disk and it has to get the data back onto it. That process of getting the data onto it is called resilvering.
Instead of remirroring or something like.
Yeah, it's always resilvering, whether it's a mirror or whether it's a RAID Z1, Z2, Z3, whatever, it's resilvering.
It's like bringing the new disk into the system.
So in-place upgrades. One of the things that people like to complain about with ZFS is that you can't take a 4-disk wide RAID Z1 and add a 5th disk and now have a 5-disk wide RAID Z1. You cannot do that. It is not a thing that can be done. However, if you want more capacity, what you can do is you can put a bigger disk into each slot, that 4-disk RAID Z1. And at the end of it, if you go from 4 1-terabyte disks to 4 4-terabyte disks, you will have quadrupled your capacity once you replace the very last disk in that array. You can do that for any type of VDEV. However, nothing happens until you replace the very last disk in that VDEV. So let's say you have a 16-bay system. If you have a pool of 8 2-disk mirrors, you can get a capacity upgrade every time you replace any 2 of those things. But if you had one single 16-disk wide VDEV, you're going to have to replace all 16, waiting for a resilver after every single one of them before you finally see the capacity increase at the end.
So that last resilver, you see the bump in capacity. Can you walk through the commands to do that? How do you actually that last resilver just magically makes it available to you and you can then format it, or what?
There's no formatting involved. You've already fed ZFS the disk and it's resilvering, and once it realizes that all the disks in the VDEV are that capacity, then the VDEV becomes that capacity.
Matt Arrington talked at BSDCan about the work he's doing enabling online RAID Z expansion.
Yeah, that may happen at some point, finally.
Probably next year in alpha.
Yeah. Keep in mind that that's an inherently very dangerous operation, and danger is kind of like the exact opposite of what you usually want or expect out of ZFS. So in the real world, doing an online rebalance like that, changing the topology of a VDEV, that can be something that sounds attractive if you're just kind of playing around with it at the house. If you're doing anything serious with ZFS, and if you've got 12 or 16 disks to play with, you should be serious. That's really not a grown-up move.
Well, the feature is live now in Delphix's version of OpenZFS.
Yeah.
And there should be.
Yep, a lot of people ask for it, but again, if you're treating your storage like a grown-up, don't freaking do that. It's dangerous. You're gonna have a big impact on performance while you're doing it because you're gonna be lighting up every single disk to read and then every single disk again to write, and it's dangerous. Do not recommend. Yeah, it can be done, and yeah, if you're just kind of playing around, and at the end of the day, also if you're a grown-up, you should always have a backup, but you should be prepared for the possibility you may have to go to backup if you're doing an online, resizing, reshaping of a Vita. That's a very dangerous operation, and it increases the likelihood that you might lose that board.
Why would you not just add more VDFs?
It's exactly what you should do. Or if you absolutely need to just reconfigure absolutely everything, then you build a new system with different disks and you replicate onto that one, and then you decommission the old one and do whatever you want to. And
Something people ask for, and they've worked on it.
yeah. All right, so we talked a little bit about this. I use the word tracks or trends toward when I talk about the IOPS of these various configurations for very good reasons. It does trend towards that. A RAID Z1 stripe will trend towards one disk of performance, but it may not actually get there. A pool of several RAID Z stripes will trend towards the number of VDEVs worth of IOPS, but it may not actually get there. Or in some cases, it may do a little better. Some reasons for that. We talk about RAID Z variable stripe writes. If you're using RAID Z arrays, you may actually be able to not have to light up all the disks for these horrible little small block writes. So that can improve things a little bit. You can decrease things, particularly if you're using solid state disks because they perform so insanely well. You can just saturate the SATA or the SAS bus, SATA or SAS bus. If you have if you got a pool of 8 solid state disks and 2 disk mirrors, it very frequently will not outperform a single solid state disk because that disk already outperforms the controller that all those things are plugged into. So you'll bottleneck on the slowest thing you got. You can also saturate the PCI Express bus. If you've got like 16 or 24 high performance solid state disks, they are faster than the motherboard's PCI Express bus. You will not hit your theoretical maximum there. The ARC, that was one amazing thing about ZFS I didn't talk about. ARC stands for Adaptive Read Cache. So every file system you have ever used has a read cache. If you read data off the disk, it stays in RAM even after you said you were done with it. That's so that just in case you want to ask for that same data again, it doesn't have to waste those IOPS on the storage. It can just grab it out of RAM, which is much faster, frees up those IOPS for other things on the storage. It's amazing. The problem with that is every other file system you've ever used, whether it be DOS, NTFS, the various abominations on those glowing fruit things you guys like, you name it, they all use the exact same type of cache. It's a least recently used cache, meaning that it just keeps adding more things to the cache, and the oldest thing in the cache, once the cache is full, gets thrown away. And it doesn't matter if you have asked for that that least recently used thing. It doesn't matter if you've asked for it 5,000 times since it's been in cache. If it happens to be the least recently used, at the moment that you read some new piece of throwaway data off the disk that you'll only ever use once, boop, it's gone. The adaptive replacement cache, if you look it up on Wikipedia, you can find more information about the logic that I won't bore you with. You can think of it as a weighted cache. The more frequently you access data out of the ARC, the harder it is to dislodge it. Almost like that data is getting heavier. It's harder to push out. So the net impact of that is, say you're running a Windows Server VM maybe, and the storage is on a ZFS data set. Well, that server is going to be accessing the same freaking libraries over and over and over again. And it's going to be really, really hard to push those out of the ARC. Where if Windows was running on the bare metal, it would be throwing them away constantly as you read, a cat JPEG or, whatever the heck every now and then. So really strangely, what you'll see is that when you run Windows virtualized on top of ZFS, the seat of the pants is it blows the freaking doors out of Windows running on the bare metal on the same machine because the storage cache is so much better. So that's the ARC. And the more you read things out of the ARC, the less you're actually committing a read IOPS to the disk, the faster everything goes that does have to hit the disk. So that can change what your IOPS looks like. The slog, the secondary log device, somebody from the back asked a while back about, is there some way I can add an SSD to a bunch of Rust stuff and, kind of just jam it all together and make it faster? And sort of yes, the answer to that is a slog. Slog is secondary log device, and what that actually means is, we talked about coalescing or aggregating writes before. Well, that's fine for asynchronous writes. Most of the writes that you do to your file system are asynchronous, and basically the file system is allowed to hang on to that in memory for as long as it feels like it needs to before it actually flushes it out to the disk. And that allows it to optimize those writes to minimize the impact on your storage. A synchronous write is a different story. When you're running a database, databases want synchronous writes. When a database says, I want you to write this data, it's not kidding. It wants it on the disk now, buddy. And it's not going to do anything else until you tell it, yes, sir, I have written your data to the disk. That's a synchronous write. If you have a slog device, which is going to be a fast SSD when your pool is rust, then you can do what the database wants you to do, and you can commit that to the slog, which is fast in SSD, and say, yep, I got your data on the metal. And the database can go on about its business. And as the stuff aggregates on the slog, then you can push it out to the rust, which is much slower. So you get the benefits of asynchronous looking writes, mostly, sort of, when you're actually doing synchronous stuff. Fragmentation will screw up your IOPS because you're just all over the place looking for this stuff. Pyder topology obviously will change it. All this kind of crap. Again, most of these things hurt you rather than help you, but the point is that it's not just as simple as saying, well, I have a disk rated for 200 IOPS and I have 4 disks in a RAID 1 and therefore I will get blah. It's not that simple. It never is. You can estimate what it's going to be like, but you can't just punch it into a calculator and get exactly what you'll have. A-shift is really important on ZFS. A-shift is a really funny way of saying the hardware block size on the underlying disk. A-shift is set per VDEV, not per pool. However, if you screw up your A-shift setting on any given VDEV, you have screwed up your whole pool, because once a VDEV is created with a given A-shift, it's an immutable property. And as we know, for right now, Matt is sort of kind of working on something that will allow you to remove a VDEV from a pool. By the way, well, I wouldn't say don't tell Matt I said this, but he knows my opinion on it. It's a bad idea. Don't do that. That's like an emergency last-ditch thing. I know you're going to bring it up. There is, right now, you can't ever remove a VDEV from a pool. Once you have created a VDEV, you have that VDEV. The only exception is if you oopsie and add just like a single disk as a VDEV to your pool, your way around that and not having your pool forever be at the mercy of that one single disk, you can add a disk to a disk and make it a mirror VDEV. You can also add another disk to a 2-disk mirror VDEV and make it a 3-disk mirror VDEV. That's the one kind of VDEV you can actually make wider. But yeah, so the A-shift is supposed to match the underlying block size on the drive. And this is actually bits, right? So A-shift equals 9 means I've got a 512 byte block size, like old school hard disks, right? A-shift equals 12 corresponds to 4K sectors, like most modern hard drives are. And some SSDs have 8K sectors. In particular, if you do the Samsung 800 or 900 series, either Evo or Pro, they have 8K hardware sectors. Now, where this gets difficult is hard drives frequently lie. They will tell you, oh no, boss, I got 512 byte sectors. And the reason they do that is because Windows XP only understood 512 byte sectors and would barf up a lung if you fed it a disk that said, I have 4K sectors.
VMware.
So some of these disks lie. Yes, you keep saying VMware. So you have to be careful about this. You don't want to just assume that ZFS will do the right thing. It will try, but if your hardware lies, ZFS won't know any better. In particular, those Samsung SSDs, which are fabulous SSDs, lie. But if you don't tell it A-shift equals 13 when you're creating it, you'll end up with A-shift equals 9. And when you tell an 8K device that you want it to write data 512 bytes at a time, now your super fast 90,000 IOPS SSD may get outrun by a Western Digital black hard drive. It's that bad. So don't screw this one up.
But can't you do create another pool and transfer it?
Yeah, but you have to throw away the pool that you had. You screwed that pool up. You can replicate it all onto another pool and it'll be fine. But that pool, it's garbage now. If you're not sure about A-shift, guess high. If you take a 512 byte device and you tell ZFS, I want you to write to this in 4K sectors, your performance penalty is basically nothing. The only thing that's going to screw up is you'll have a little bit more slack space, because now, rather than if you write 511 bytes of data, you've got 1 byte of wasted space in that 512 byte block. Now you've got 3.5K of wasted space in that block. Boo-hoo. How many 512 byte files do you have anyway? It really doesn't amount to anything. We talked about the slog. If you're using Rust, you should absolutely consider a slog. It will help with synchronous writes. However, if you're not doing any synchronous writes, if you don't have any databases or anything like that, they're going to demand immediate writes, a slog will probably not help much. It's not just an automatic win device for making writes super fast on anything. It only really helps if you've got a lot of synchronous writes in your workload to begin with. Some of you who already know about ZFS, probably a gentleman in the blue shirt in the back, will know all about L2 ARC. That's where you can take a fast solid state disk and make that be cache for all of your slow Rust. Don't use it. There are some workloads that benefit from L2 ARC. None of you have one. Your best case is L2 ARC won't hurt you any and it won't help you either. Very frequently it will slightly degrade your performance because the problem is now instead of using your RAM, your nice super fast RAM, that's at least 2 orders of magnitude faster than the fastest solid state drive you have available to you. Instead of using that to put your actual data in, now you're using it to index this solid state drive. So everything goes, it's now much slower. So yeah, no ARC, no L2 ARC.
If I have that the right way, is that the way the hybrid drives are working then?
Not exactly. Have you used the hybrid drives much?
No.
They suck. They're not any slower than the regular conventional drives. They're really not any faster. I got a couple of them just to see, and no, I mean you've got like 0 seat of the pants difference. They suck. And no, the way those work, there's no ARC involved there. I mean all those is just literally as you read data to some degree, they're going to store a copy of that data on that solid state disk so that hopefully they can maybe serve it out of the solid state instead of out of the Rust, but it's always a pretty small amount, and also it's not an ARC, it's that least recently used, so it's really, really easy to push all the valuable crap out of it. In an actual practice, it's exactly what happens. You could get super duper lucky and have the exact right workload that will actually have you reading everything out of that tiny little solid state buffer, but if that's the case, then you only have a super small data set and you should have just put that on a solid state disk to begin with.
So if you use the same configuration but you change that to be ARC, would that...
What's ARC stand for?
Yeah. If you actually had an ARC-powered hybrid disk, that would help a lot. For the same reason that the ARC is a lot better than an LRU cache to begin with. I know absolutely nobody doing that though.
What's ARC stand for?
Adaptive Replacement Cache.
Thank you.
All right, ZFS has built-in compression. It is sadly not the default. When you create a pool or you create a data set, it sets by default compression off. That's bad. You don't ever want compression off. Set compress equals LZ4. In your absolute worst case where you have absolutely completely incompressible data, what will happen is the first couple K of that completely incompressible data will not get a compress ratio worth talking about, and ZFS will stop trying to compress it. And you'll have absolutely no performance penalty from that. Even when all you're writing is completely incompressible data, if you have compress equals LZ4 set, guess what it can compress? Remember we mentioned slack space before, that wasted space at the end of sectors when you have an uneven amount of data? That stuff gets compressed. So it ain't a whole lot, but you'll save a little bit of space. And the other nice thing about it is, it actually saves you performance. Modern CPUs can compress data LZ4, or fail to compress it in the case of incompressible data, much faster than you can read it out of the storage array. Yes, this is true even if you've got a $50 AMD Tinker Toy APU and a really fast Samsung Pro solid state drive. It will read and write data faster with compress equals LZ4 on than it will without. I know this because I tested exactly that. Yes?
Will that by any chance cut into the CPU power that could be used for other things?
Teeny tiny bit. Not enough to notice even on that little $50 AMD Tinker Toy I mentioned.
What about like a low power ARM type chip? Is it still just really truly negligible?
You would want to benchmark that. On like a really low power ARM, benchmark it.
Dual core 1.6 gigahertz, that type of range, somewhere in that ballpark?
Now, I would expect in that ballpark, LZ4 is probably almost certainly still going to be a win. I mean, how fast is the storage on that dinky little ARM?
It actually has access to the SATA. So
sure, but I mean, are you plugging like a super Whamidine you know, 120,000 IOPS solid state drive in your dinky little arm?
Yeah.
Yeah. In some cases you might, but yeah, in the back.
So unlike the RAID Z, is this something you can turn on and off after you got started? And
Yes.
you back? Okay.
Now, with that said, if you've got a terabyte of data on storage, and now you set compress equals LZ4, it is not going to go compress that terabyte you already wrote. It's going to start compressing new data.
Okay, so that's different than Microsoft and Windows land, where you tell it to turn on drive compression, and in the background it goes and.
Yeah, it won't do that. If you want to compress already written data, what you can do is you can turn compression on, and then you can replicate the data from that data set to a new data set on the same drive, and that will thereby make sure it all gets compressed along the way. You can also just do like some wacky Flintstone stuff and just read files and write files or whatever. Anything that modifies it will, once it writes back out, it will write compressed. Compression is also, it's not something that stays in place when you replicate. It's going to honor whatever the setting is on the target. So if you replicate data from an LZ4 compressed data set onto an uncompressed data set, it's going to uncompress, or the other way around. If you're on Linux, you probably want to set ZFS set xattr equals SA. That means you want to store extended attributes directly in the inodes, not in special files, hidden files in the folders. It's a significant performance bump if you've got a lot of relatively small files, like say for example, if you want your home directory to be on ZFS, you should totally set xattr equals SA. It will improve performance dealing with all those little dinky files. Now if you're storing VM images, and you've got like 8 VM images on the disk, you know, each of them several terabytes in size, in theory that's still a performance win. In practice, it's not going to do enough to matter.
What does SA stand for?
I don't even know, but what it actually means is store the xattrs in inodes, the extended attributes in inodes. A-time equals off. Set that. Please set that. A-time is access time, and if you leave A-time on, then every single time you look at a file, it's going to have to write to the disk to update the time that you last looked at the file. Do not double the IOPS that you're committing to your storage. Set A-time equals off. Do you really care the last time that you read a file? You don't. So turn that off. Okay, so in a lot of cases, you're going to want a smaller record size. The default record size in ZFS, and record size is not the same thing as A shift, is 128K, which is kind of a compromise. It can be anything from 4K all the way up to 1 megs. The default is 128, which isn't horrible for anything, and it's not great for anything either. If you're doing database binaries or VM images or anything that might have a lot of small I/O, you're going to want a record size equals 16K so that you're not forcing it to read in bigger amounts of data or write out bigger amounts of data than what it actually needs. So this will, in that case, it will greatly increase the amount of performance you get out of your system. Now the exception to that is, you'll notice down here I said lower record size may not be for everyone. Please consult your sysadmin before taking. The exception to that is if you've got a lot of really large files that you're only interacting with as large files, like say a bunch of movie files or a bunch of photos. You know, they're all from your camera and they're at least 4 megs or whatever. You don't want a small record size on those because you're not modifying little pieces of them back and forth. You're not saving or reading little chunks of data. You're only reading it like 5 megs at a time. So in that case, on that data set, all these properties are per data set. They're not for the whole pool. You want to set record size equals 1 meg then for the directory that you've got, you know, a terabyte worth of images that, you know, came in raw off your Canon, or even, you know, just the 4 meg JPEGs that came off your smartphone. There's nothing smaller than a few megs, and you're not accessing it in little pieces. You're only pulling it in and out in those big chunks, and you want a big record size, 1 meg. If you're not sure which one you want though, go small. Because when it really hurts you is when you're doing the small access. And where this really helps you is when you're doing the small access. So when in doubt, you always want to tune for better performance where the pain is. It doesn't matter if you improve performance where you already weren't unhappy with your performance, but you know, if you're decreasing where the performance where the pain is, to make the big number even bigger, you're going to make your life miserable. Take snapshots. So we talked about this before. ZFS snapshots being able to preserve everything. This is my actual workstation here. You can see I've got 436 gigs of legally acquired movies in my movies directory. And you can see me time ZFS snapshot data movies at 1. It took 0.15 seconds to take that snapshot. Now you see time RM-RF movies, where I delete all 436 gigs of movies. That took me 12 minutes and 9 seconds. This is on Rust, it's not on solid state. Now you see time ZFS rollback data movies at 1. That snapshot I took before I deleted frickin' everything, 0.65 seconds to bring back my 436 gigs of data that I destroyed. And it's all back, all 436 gigs. That would look the same if rather than deleting the movies, I had actually piped data from dev/urandom over every single one of them. It wouldn't matter. That rollback would still just be, and all that damage is undone. So if you have ever worried about Locky or all the other various names of all the, Russian gang, encrypt all your crap malware, this is your fix. Rollback, damage undone. We have here a Windows virtual machine. Our Windows virtual machine is running on top of ZFS. It's a QCOW2 file on a ZFS data set. This is a very valuable PDF of an article I wrote at Ars Technica. That is a copy of Locky that I just ran as administrator. Notice this decrypt file just popped up, and all these just changed to notepad icons, and now the content of all of them is instructions on how to send a whole lot of Bitcoin to all these jackasses in Russia or Moldova or somewhere. All of them. It's all garbage with ransom note. Oh no! What will I do? Worse off. There's my snapshots. Roll back. Boot our VM.
Windows jerk rescued. Yay!
Voila! All my crap's back.
How much space does a snapshot?
Yeah, that's the.
So what you need to understand here is that ZFS is a copy on write file system, right? So what that means is when you tell ZFS, okay, this block of data right here, I want you to change it. I no longer want it to say jerk face, and I want it to say jerk Y. Now, you're telling your file system, replace this with that. You tell ZFS that, and ZFS says, yep, I've done exactly what you asked for. It lied to you. What it really did is it wrote jerk wad over here, and jerk face is still right there. Now, jerk face is unlinked, actually, and it's made available again. But the important part is we didn't write over it. We wrote a new thing here, and then we unlinked it there. Now, what this makes possible is when we say ZFS snapshot this data set, what actually happens is now every single block that's live is marked immutable. Now, we've taken a snapshot, and I say, take this one right here that says jerk wad and make it say jerk face. And it says, all right, it's exactly what I did. It's still live. Now I have a block over here that says jerk face, not jerk wad. And now this one is linked in to my existing file system, but this block's still here because it's marked immutable. And all these blocks over here, including this one that we didn't unlink when I said to change it, are still marked as belonging to snapshot at 1. So now I know this whole collection of blocks that are tagged at 1 are still there. And if I want to go back to the condition I was in when I took snapshot at 1, I just say at 1's the live file system now. There it is. So that's the way a rollback works. Yes, sir?
So I can't tell you what file system level it was, but I remember there was a Linux problem where system admin we had our file system, and we started running out of the things that linked the files together.
iNodes.
Okay, iNodes. Is it related at all to the link to the files that you just described or not? That's
No.
an OS layer versus a file system?
So iNodes are what contain the metadata information about individual files. And when you create an ext4 file system, by default it creates so many iNodes per block of storage available in the file system. And if you write lots and lots and lots of individual files, you can run out of iNodes even when you've still got lots of space left. When you build DKMS kernel modules, this will happen a lot, because if you got like a 60 gig file system and you're not removing old kernels as quickly as it downloads and installs new kernels, you end up with like 50 kernels sitting around. Well, you've got the headers for every one of those 50 different kernels, and it's tons of teeny tiny files, and now you've got like 40 gigs free in your file system, but you can't write anything to it because you're completely out of freaking inodes. And you can't get them back until you clear all those old kernels, those old headers.
Now, the linking that you just described of making updates in this file system are all in the data portion of the file system, and they're not managed by the operating system, and it's not a allocatable resource. It's just using space on the
Inodes are at the file level.
Yeah.
What we're talking about with snapshots are at the block level. The snapshot is a linked list of blocks belonging to the file system, not files. Doesn't know about files, doesn't care about files. Includes the metadata used to describe the files within the file system part of it. Matter of fact, you can create a ZVol rather than a data set, which is nothing but block level storage. You can format that ZVol with ext4 or NTFS, like that Windows that you saw, or what have you. It's still snapshotable. It's still treated like ZFS. It's still the whole thing, but the blocks are presented as a block device to the file system that does its own file system things on it. ZFS can also be a file system under the block management part, like when you have a data set and you save files on it. But again, all that you're talking about with inodes, that's the file system level, not the block level.
So to be clear, does the snapshot expend any storage at the moment you make the snapshot? Or tiny, but it grows?
Teeny tiny
It grows as you now make modifications.
Exactly, because what happens is, so right now, you say, I've got my 1 terabyte of data. You say ZFS snapshot at 1. Bam! Now, in addition to the very special snapshot that is actually the live production file system right now, you have a new snapshot called at1. And all these blocks are tagged as belonging to at1 as well as to the live file system. You don't change any data. You say ZFS snapshot at2. Now they all belong to at1, at2, and the live file system. It hasn't really consumed any data. It's just multiple membership to all these things. Now you delete 10 megs of data, and you say ZFS snapshot at 3. Now what's happened is you've deleted these 10 megs of data. They don't belong to snapshot at 3, and they don't belong to the live file system, but they still belong to 1 and 2, so they haven't been unlinked. They're not available to be rewritten to you yet. Make sense? So the more these snapshots diverge from the live file system, the more space they will occupy. As long as they are convergent with the file system, they occupy no space.
Where is that membership information stored, right? I mean, if you're a member of at1, at2, at3, what if you were a member of thousands? Like, where is this logged and recorded in the file system, or?
I invite you to read the source code.
Cool.
I don't know enough of an answer to that to answer it intelligently, so I would rather say you're going to need to read the source for that.
Yeah, I guess I'm just trying to understand if each block has the ability to be or not be a member of a particular snapshot.
It's a linked list per dnode. It's in ZFS underscore dnode.c.
Yeah, I mean, I can tell you snapshot's a linked list, and the live file system is also a linked list of block pointers. But when you start going into, well, where exactly is that linked list stored? I don't know.
Well, the very fact that it's a linked list basically tells me it's
Yeah.
official.
Okay. You had a question.
Yes. If you took the snapshot and then deleted files, the actual information wasn't deleted. So what was happening during those 12 minutes that it took 12 minutes where
That was a lot of blocks. It had to mark every single one of those blocks as no longer belonging to the live file system.
Okay.
So it had to go through and it had to update. I mean,
Well, the
it
RM
wasn't updating
was
blocks,
running at the
right?
file system level, not at the block level, right?
Well, it was running a little bit at both, because it both had to update all the metadata in the file system, and on the block level, it had to tell the live file system, it had to unlink all those blocks from the live file system, even though it was not unlinking them from the snapshot I had just taken. So you've got a little bit of both going on. And the majority of that time is most likely, yes, at the file system level, messing with the directory structure and yada, yada, yada. But it boils down to, that's a lot of files you got to stat, it's a lot of blocks you got to touch. Yes?
I guess why was there not the same delay when you restored the snapshot?
Well, actually, that goes back to tell us for sure that our issue was So that was a great question. And you actually just answered the question of is it the file system level or the block level. So the file system level stuff took 12 minutes and 9 seconds. The block level stuff did take an amount of time. It's the difference in that, 0.15 seconds it took to take the snapshot and 0.65 to roll it back. Well, that half a second is how long it took to say all these blocks belong to the live file system again, basically. But it doesn't have to regenerate all the metadata at the file system level because all that metadata is just put back. It still existed, so it was just put back exactly like it was. Whereas we had to actually make the metadata changes inside the file system level to RM. But it would work the other way around too. If we could RF all those movies and it took 12 minutes and 9 seconds, but we take a snapshot and we copy them all back in from somewhere else, I could roll back and get rid of them in the 0.651 seconds too.
This rollback, the way that this example is illustrated, it's occurring on the live volume, is that correct?
Yeah.
Awesome. Gotta give sure some people sticking around, man. This is sure. No, obviously the content's very good. So.
All right, what's up? Somebody had a question.
Yeah, right here.
Yeah.
You were talking about the, what do you call it, the encryption ransom stuff?
Yeah, ransomware.
Ransomware. Okay, so you can actually use ZFS as your base file system for
virtual machines.
Well, no, I'm not talking about regular machines. Your hardware machines.
So as
for
the
your
base
virtual
file
machines,
system.
for virtual machines, I understand.
Yeah. So it is possible to do a ZFS root on Linux systems. I don't generally recommend it. It's more trouble than it's worth.
So it's mostly for like virtual machines.
Well, no, because what you can do is
servers. Okay, I'm sorry.
What you can do is, most people on their machine, almost all the data they truly care about is in their home directory. You can make your home directory ZFS.
Okay.
The root disk, while it can be made ZFS, you can boot from ZFS. Right now on Linux, it's more of a pain in the butt than it's worth. If something goes wrong because it has to be built, the DKMS module has to get rebuilt with every kernel version, it's way too likely something will screw up and you can't boot your machine. You have to recover from another one and screw all that, because here's the thing. You don't care about your root file system. There's nothing there worth a crap. You can restore that in 15 minutes from a thumb drive. Your data is what you care about. So put your data on ZFS and don't worry about the root file system. All right, so I'm almost done here, I promise. We're talking about why we want the snapshots. So what's the problem with these snapshots? If you got the ransomware, or you made the stupid mistake, or the thing went wrong and you hadn't already taken the snapshot, well, it's too late to take it now. The stuff's already gone, right? So you want to make sure you take those snapshots regularly. And I wrote a tool called Sanoid that makes that really, really super easy. This is a Sanoid config file. You can see we got 3 modules here. This is actually from, it's not this machine, it's from my workstation at the house. Data, use a production template, use it recursively. That means if I create new data sets underneath data, like data images, data movies, whatever, these policies will be applied to those automatically. I've got a separate one for my my actual phone, which backs up by rsync on my machine, and that is the actual production template, which says I want to take and keep 36 hourlies, 30 dailies, and 3 monthlies. I don't want to take a yearly snapshot. I do want to take snapshots automatically. I do want to thin them automatically. So that and one single cron tab line that just says 5 stars and Sanoid -- cron. That's all you need, and it will parse that, and it will do all those things. Every hour on the hour, it'll take a snapshot. If you've got 36 snapshots hourly already, and you take another one, it'll get rid of the oldest one, as long as it's more than 36 hours old, because Sanoid is very paranoid and very careful. Same thing for the daily, same thing for the monthly. So all you have to do is that one file right there, and know that all your crap is saved. You'll be able to step back in time on an hourly level for 36 hours. You'll be able to step back in time on the daily level, 30 days, on the monthly level, 3 months, and you don't have to worry about it.
Wild guess, how much of what percentage of your storage space is tied to the snapshots?
All of it?
Versus not having, no, if you did not
it's tied up with snapshots. So it's gonna depend on your workload and how much
No,
you
I know.
change your
I'm just saying
data,
on yours.
but understanding that, in practice, a policy like this will usually result in occupying about 40% of the space of the overall volume of data for most general purposes, whether it be Windows VMs or just raw files that you're doing the thing with. Now, if you never change it, then you'll have almost no space taken up. But what I find is that, you know, whether it's me monkeying around with a machine or whether it's an office of 20 people hammering on a file server and, you know, some virtual machine images or whatever, usually about 40% is a pretty good rule of thumb for that particular policy.
Is this downloadable from somewhere obvious?
Absolutely. Just Google Sanoid or go to sanoid.net.
Got it.
It's GPLv3.
Got it.
Can we selectively restore a file rather than restoring everything?
Yeah, absolutely. You can clone snapshots. We didn't talk about that before. You can say ZFS clone data images @1 data temp, and now you'll have a completely readable and writable file system on data temp that you can go to and you can peel things out of. If you've got like VM images or database binaries in there, you can actually spin those up and work with them live, and they won't complain because they can't write, because they can write. You do whatever you need to with it, then when you're done with it, ZFS destroy data temp, and you get rid of the clone, but not the snapshot it was based on. You can also go directly into the snapshot on a read-only basis, which frankly I usually don't bother with because it's so easy to just clone it and you don't have any surprises, and you it's a better workflow. So yeah, I mean, this is a machine that I use Sanoid on, and you can see, you know, data files work, and I got my 3 monthlies and I got a bunch of dailies, and I cropped it because I can't fit all the hourlies on the screen, but it's right there. Let me see here. Let me drag a terminal over there. Awesome.
The stupid things you never think about. So 5 stars in cron is hourly?
5 stars in cron is every minute. The default granularity of cron is to run once per minute. 5 stars means every single time, you know, whether it's minute, whatever, you know.
I thought it would be every minute.
So yeah, it runs once a minute. You don't have to run it that frequently, but I have built it to be smart. It has caching of, like, you know, how it lists the snapshots. Everything is in there basically to make it so that for most people, that in some cases you may want to run it less frequently, but for most people,
Sanoid handles doing it hourly.
yeah, but for most people, you can just every minute, and that way, one of the other things I mentioned, Sanoid is it's very paranoid, and it's a lot smarter than you might think it was. Let's say that you have a machine like a laptop, and you say, I want to take these hourly snapshots, right? The only thing is, this machine's not always on right exactly at the top of the hour when the snapshots will normally be taken, right? Well, if you've had your machine closed and off for the last 3 hours, and you open your machine at 15 minutes past the hour, as soon as it wakes up, it's going to go, it's been more than an hour since I had that snapshot. I'm going to take one right now. And then 45 minutes later, at the top of the hour when it normally should, it will take the next one. Same thing for the dailies and the monthlies and all that. So yeah, I was going to show you on this laptop itself. You can see, yeah, I can. I'm gonna have to drag it back over here because, man, coming back like over your head is tough. Nope. This way, thank you.
Oh.
All right, give me a sec. I think I have to actually close this one. No. Oh yeah, does that work on terminal?
Yeah, it should.
Oh yeah. How about that?
It's not on screen.
No, I know it's not on screen. One thing at a time. So there we go. I mean, I've got Sanoid running on my freaking laptop. So those are snapshots that Sanoid took on my laptop. It's been taking the whole time I've been sitting here in Raleigh today.
Can you cap the data necessary for snapshots? In other words, can you say, I don't want it to take up more than X amount of room if I'm doing like crazy amounts of?
No, you can't. And the reason that that is a decision on my part. In theory, I could have coded to do that, and I considered doing that. But what happens if you do that is you now do not know how much time you have that you can go back and what you can restore from. You're now in this nebulous, I don't know, maybe I got the data, maybe I don't position. I'm like, I just made a command decision. No, we're not supporting that. If you run out of data because you're keeping too many snapshots, then you're gonna have to change your policy to accommodate, or you're gonna have to increase your storage to accommodate. But we're just not even going to support this. Well, I don't know. Maybe I got, you know, maybe I got snapshots there, maybe I don't. We don't do that.
What is that data size in relation to? Like for instance, that bottom one, 1.53 meg.
This is the amount of data that is occupied only by this snapshot. So you see the 6.91 gigs here? That is the size of that actual Ubuntu Trusty VM. That's the entire reference size of it. this individual hourly snapshot only has 1.53 megabytes of unique data within that snapshot.
Now, that will change over time, right?
Yes.
Okay, that 1.53 meg will grow.
But you'll notice how it's all relatively close there, except for the places where it's 16K, which is actually the minimum size that snapshot will occupy. Now the reason for that is that when this VM is not actually up and changing and yada yada yada, only the 16K. The other thing, the reason that you don't see a whole lot more data occupied by the older ones, which you might naively expect, is you remember I said this is the amount of data unique to this snapshot, not just where it diverges from the current file system. No other snapshot can reference that data either. That's the unique data. So if I destroy that snapshot, I will reclaim this amount of data. If I destroyed all the snapshots, I would recover a whole bunch of data, even more than if you added up that individual number for all of them, because we'll also get rid of data that was never owned only by a unique snapshot. It was owned by like 5 of them at once. All right.
I noticed there's a bunch at 1 3/4 roughly, and then there's that 1 at 5.
Mm-hmm. Well, I mean, it's an entire virtual machine. Stuff's going on. It downloads updates. You know. Go away, little terminal. We'll get back to our presentation. You're so close to done, I can taste it. Use Syncoid. Syncoid automates that awesome ZFS replication I was telling you about, which by itself, ZFS replication is pretty painful to do. You got to figure out what snapshots do I have on this machine, what snapshots do I have on that machine. Let me build my command line to say I want to go from the oldest one that I have in common on both to the newest one on this one that I want to be on that one. And then I'm going to pipe it through SSH to get there. And if I want inline compression, I'm going to pipe it through LZO. And if I want buffering, then I need to pipe it through mbuffer. And each of those need their own arguments. And by the time this is all done, you've spent 15 minutes of skull sweat trying to figure out what you've done and screwing it up 3 or 4 times. Instead of that, use this wonderful tool, Syncoid. Syncoid makes it as easy as SCP or rsync. You just say Syncoid source to target. The source or the target could be local, or they could be remote over SSH. It doesn't matter. Syncoid will figure it out for you. It could be an initial replication where you're doing a full and you're saying ZFS send dataset snapshot to the remote location, or it could be an incremental where you're saying ZFS send from snapshot 1 to snapshot 2 and pipe that over there. Doesn't care. You don't have to worry about it. Syncoid will figure it out for you. Syncoid root at production, Rust shares to local Rust shares, and it just does it. Gives you a progress bar, gives you inline LZO compression, which is pluggable. You can use gzip compression instead if you've got a slow link and you don't mind burning up some CPU. It gives you inline buffering. It does all the logic. That's all you have to do. And watch, this was a real actual demo. I went through and I colored it to make it bold, but I didn't make that up. That was actually me running that command. That is over an SSH link. It's not even a local link. That machine is on a different network. We're going across the internet. That is 2.56 terabytes of data with a little under 40 megs of change data in it, and we replicated in 2 seconds across the internet. Try that with rsync sometime. It will not go well.
What is the 2.56 aside from the bold green at bottom?
Up there in the used, see I said ZFS list Rust shares,
Okay.
and it tells me there's used 2.56 terabytes in that data set.
Okay.
So that's the size of the data set we replicated. It's an incremental replication, and it only changed by this 38.6 megabytes you see of data that actually moved through the pipe. Point is, the whole thing synchronizes 2 seconds across the internet. Yes?
Does that require ZFS on both sides?
It absolutely does. Which is the best excuse for just not using things that aren't ZFS, because they suck and you don't want them.
Yeah, I was thinking more of backing up to the cloud, but...
Yeah. Well, you know, what you can do is you can get yourself an rsync.net account. And despite the name rsync, they offer ZFS-backed storage, and you can use Syncoid to get there. I see the gentleman in the blue shirt just having conniptions back there. Why do you hate rsync.net?
Well, there's nothing in the ZFS receive code that prevents you from doing malicious things.
Yeah, at the moment there's not. So you do have to trust rsync.net if you do that. You will be in the
They have to trust you, and you shouldn't trust them for trusting others.
Yeah, you do have to trust them as, I mean, most of your backup schemes to Amazon that people are using are unencrypted, and they're trusting whoever. I mean, yeah, you have to trust them with the raw data. Right now, but I can't believe this is the one time the gentleman in the blue shirt hasn't mentioned the freaking code coming down the pike for raw encrypted send. where it can be encrypted, it can stay encrypted, and the host on the other end never has to have the key.
I'm not that interested in the encryption, I guess.
And yet you brought it up the same way. Come on, man.
It's not, no. The receive bit is about the encryption. It's about the fact that you can send malformed send streams and trigger problems or buffer overflows or cause it to write incorrect data. The receive code isn't. I mean, it's no different than any other file system. It trusts the disk, which the receive stream is in that sense. So.
Well, the receive stream's kind of nothing at all. I mean, the send is what it is, and the receive just pipes that into ZFS. I mean, at the end of the day, you either all of your data matches the checksums for each of the blocks, or it doesn't. It's still checksummed in the stream that you're piping into receive. Yes. When you do ZFS send, you are sending checksums for every block that you're sending.
And metadata.
Yes.
Which is also checksum, but the metadata can be maliciously malformed with correct checksums.
Mm-hmm. Yeah. Believe it or not, we have actually made it through this monstrosity of a slide deck. I hope you guys have had fun.
That's not for the end, that's for me.
Say what now?
That wasn't for the end of the show, that was for you.
Thank you.
Yeah.
Yes, sir.
You had touched on earlier about the licensing and Scott McNeely and Oracle. Can people put ZFS in a product, or does everybody have to add it on?
Can do.
So,
you seem to say they could, but it looks like they can. So what's the border there?
So we get fairly deep into license geekery here. The Cuddle is a weak copyleft license that is incompatible with the GPL, which is a somewhat stronger copyleft license. They both conflict with one another, which means that you can't have one single code base that combines both GPL and Cuddle code, because you'll be violating the GPL in terms of doing so. As I recall, you're not actually violating the Cuddle if you do that, but you are violating the GPL. I'm not 100% on that. You might be violating the Cuddle also. I'm not as familiar with the Cuddle. But at the end of the day, so you have this thing like, I can't mix my chocolate with my peanut butter, right? I got the GPL stuff over here and the Cuddle stuff over there. But here's the thing. Those protections only kick in on distribution. So you have a Cuddle licensed loadable kernel module over here. This is a piece of code over here. You have the Linux kernel over here, this GPL licensed, right? You as a user are 100% within your rights to say, hello GPL licensed Linux kernel, I want you to load this Cuddle kernel module. Now, if you distributed this, you would be in violation of the GPL if you distributed it all as one chunk of code, because you've distributed it. But you can run it, you can do whatever you want to with it. So that's the first interpretation. Now the second interpretation, if you want to talk to, and please don't take this word too hostilely, because I really don't mean it that way, but I don't know a better word. If you talk to some GPL zealots, for lack of a better word, like Brad Kuhn, formerly the Free Software Foundation, now of the Software Freedom Conservancy, he has been involved in almost every single GPL law enforcement suit on the planet. He believes very strongly in the GPL and maintaining the strength and enforceability of the GPL. He hates this idea, because the idea is that even though, so there's no question ZFS on Linux is over here and the Linux kernel is over here, right? But the problem is there's a shim that has to go in between these two. And the argument is that shim, which is licensed LGPL, which the LGPL is allowed to attach to non-GPL code, the argument here is that no matter what, this kernel module, because it's designed to attach to the kernel, must therefore be considered a derivative work of the kernel, and therefore it should have to be covered under GPL. Most normal human beings would say, does anybody mind a curse word in here?
BS.
Most normal human beings would say that's a crock of shit. ZFS existed completely separate from Linux for a long time, for many years, before it was ever brought in, most of the code is still the exact same code that it is if it's running under BSD or running under Delphix or whatever. It's clearly not a freaking derivative work. It's this thing over here and that's that thing over there, and this thing has a freaking API. That's what APIs are for, to attach other code with. It's pluggable. They're not the same thing. Now here's the thing. If you speak to Brad Kuhn, or I'm sure if you ask Richard Stallman, which I have not had the cojones to do, they would tell you that, no, it doesn't matter, derivative work, you can't do that, it's not cool. What you need to do is you need to get this license changed from Cuddle to GPL. So we're no longer mixing the chocolate and the peanut butter and everything's pure and everybody's happy, because we don't want to weaken the GPL. We don't want to set this precedent where we say, okay, well, you're allowed to distribute stuff that's not blah, 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 that breaks these rules. All right, now we get back into real human territory. The thing that nobody really wants to seem to talk about, and everybody seems to want to ignore, is the fact that we have been allowed to distribute completely freaking proprietary loadable kernel modules since the inception of the Linux kernel. Without loadable, completely proprietary kernel modules, you wouldn't have workable NVIDIA drivers, for one. An awful lot of industrial machine controller code has to run kernel mode and is loaded as an LKM and is completely proprietary. They are not willing to share it. And is distributed, and nobody says a word about that because they want Linux to be usable in professional circles. They want you to be able to run your 3D games and play Steam with games with good frame rates and whatever on Linux. And this requires that we just turn a blind eye to these proprietary loadable kernel modules that if you really stretch and say anything attached to the kernel must therefore be a derivative work and blah, 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 would have to be GPL. But nobody says anything about that because that would destroy the utility of Linux.
Well, I think that part of the reason why nobody says that is because Linus and most of the other kernel devs have said, stick to the API and we don't care.
Linus does not give a warm crap about you using ZFS with Linux. He absolutely does not. It irritates the crap out of him. Yeah, his position is absolutely anything on the other side, of the LKM APIs. Yeah, that's your own code. Don't care. Not worried about it. All right, so anyway, getting back into real person territory. So we have this long-standing precedent that we don't go after fully freaking proprietary kernel modules. But now we have some people that want to kick up a fuss over this copyleft kernel module. It's just not quite the right kind of copyleft. So what happens if we actually try to do a GPL enforcement lawsuit? Well, now you go into court and you take a judge who is a normal human being. He is absolutely not a Free Software Foundation employee. And you say, all right, well, let's read the code of these licenses. Now, one interesting thing about the GPL, if you actually sit down and read the text of the GPL, and this is very unusual for a legal license, the preamble to the GPL explains in very human-friendly language what the license is for. That it's to protect and enhance the freedoms of the users by making sure that this code can be distributed and shared equally for all, and enhance the blah, 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 and make the flowers grow and all this happy, sunshiny crap, right? Here's the thing, that's not a separate document. That's a legally enforceable part of the GPL. So you bring this in front of a judge or an arbitrator and you say, okay, we're in violation of the GPL by including this stuff here, and that person says, all right, well, not to do the, what little Johnny did defense, but people have been shipping proprietary kernel modules and nobody said boo for 20 years. So what's up with this? All right, well, I look at the actual legally enforceable preamble of the GPL and it says the goal is to enhance software freedoms and enhance users' ability to use all the code. Doesn't letting them do this actually fulfill that goal? This license seems to have some conflicting text and we need to rule on what the overall meaning is. So now, either one of two things happen. Now, either you have a court-enforced precedent that, yes, you can mix incompatible licenses in with the GPL if it advances the goals in the fuzzily stated, not legally super laser precise preamble, in which case the ZFS users keep using to do their stuff, but GPL enforcement cases have been significantly weakened, which is not something that any free software super enthusiastic person wants to happen. Or, now you say, no. Nobody can use this ZFS code. And now the first time you have two companies that both compete, and one of them has a proprietary kernel module for their code, the other one says, bam, you can't ship your code anymore. Your product is dead in the freaking water. You can either open source your code or you can stop shipping. Matter of fact, we're going to go get a temporary restraining order right now, and you got to stop shipping right now until we finish arguing this, which might take a year. But even if it doesn't take a year, we have precedent that says, I mean, you can't even mix copyleft code into the kernel. You sure as hell can't mix that proprietary stuff. You're done. Nobody wants that either, because now nobody wants to use Linux for their industrial stuff. They're going to use a BSD with a weak permissive license. And nobody in the Free Software Foundation or anybody else that's involved in this stuff, nobody wants that either. So at the end of the day, you have folks who are angry because they don't want to weaken the GPL enforcement stuff, complaining about ZFS, but there's absolutely no good outcome out of them trying to pursue it.
I think I've read some people complaining about the NVIDIA.
Yeah.
But it always seemed like they were restrained. They were complaining about something they had shot themselves in the foot, now it hurts.
Yeah, exactly. So that's kind of where we are with that, and I actually co-authored a presentation on exactly this topic about 5 or 6 years ago at one of Todd's conferences. Got a local IP lawyer who was actually familiar with some software license enforcement cases. Don't get me wrong, I'm not trying to say he was some giant in the field, but he was an actual lawyer, which I am not, who was familiar with doing license enforcement. And I kind of walked him through some of the technical issues and some of the relevant history. And he looked through it from analyzing the legal likelihood and what he had seen happen in court cases before. And he came to the conclusion. He was like, "Man, I think you could just compile it straight into the code, and ship it, and call it a day, and I don't think anybody'd say boo. The heck with the loadable kernel module argument." And Brad Kuhn of the Software Freedom Conservancy was in the audience, and boy, he popped out of his seat boiling mad. I thought he was going to go through the ceiling before his feet hit the ground. He was so mad. But then about another 3 or 4 years after that, you have Canonical say, you know what? We're shipping ZFS. And they have been shipping ZFS for 2 years now. And a couple of people have grumbled, a couple of people have whined, a couple of people have called them nasty names. You know how much time has been spent in any courtroom anywhere in the world over this? Who said? And I just explained to you why. I mean, there's now the one thing that I am actually concerned about. Do we have any Oracle employees in here? All right, you're not allowed to mention this to anybody at Oracle, right? The one thing I'm a little bit concerned about is I mentioned to some folks out there earlier that the Oracle ZFS code base is now completely diverged from and incompatible with the OpenZFS code base, right? In my opinion, I like the OpenZFS code base. I mean, above and beyond the fact that the evil empire doesn't own it, I just like the stuff they've been doing better. But it's very widely diverged. This becomes important because Oracle is in a unique position where they are the one company who could say, Oracle ZFS is now GPL. Now, if Oracle does that, let's say that a whole bunch of people adopt OpenZFS and it becomes very integral to their businesses, and they've adopted this as completely open, yada, yada, yada. Now Oracle says, Oracle ZFS is GPL. You people using OpenZFS are violating my GPL rights because you're mixing that stuff into the kernel, which they can do as kernel contributors and as kernel users. Now they are in a fabulous position. They decide to sue for their own evil Oracle-y reasons to force people to stop using OpenZFS, and now they have this huge incentive to go use Oracle ZFS. That I'm a little worried about.
Wouldn't that be counterproductive though? Because you talked about it earlier, there's all proprietary everything is useless and then nobody would want to use Linux anymore, so people would have to
You're missing the key
Oracle
question.
doesn't care.
Exactly. Why does Oracle care about that?
As long as Oracle has your money, they're happy.
The question you're actually asking me is Oracle willing to burn the world down for $1?
Yes.
They are.
I will let the audience answer that question. I render no opinion, but that is the question.
If you don't give Oracle $1 right now, they're going to shoot this puppy.
They're going to shoot this dog?
All right. The cane is around my neck.
Yes, I had to pull the cane. We're an hour.
Thank you, everybody.
Thank you very much.